we will talk about geomorphology and cave morphology. So I just asked the first keynote lecture to present by Aurel Perșoi. Please, Aurel. And please keep in time today because we have very short time for today's lunch. I will give you 5 minutes before and okay.
Okay. Good morning. So that because there is no time for lunch, thank you for your attention. Yeah, I guess most of you in the room know already what I should be talking about, so there is no big surprise there. At least not big surprise in the good sense, maybe in the other direction. I was a bit surprised to be asked to give this talk here, so I was not very sure whether I should thank Nadia or not, but I guess it is polite to say thank you very much for inviting me here and for offering me this opportunity to present something that I put here as yes, so I put this as a personal notes because so I put this title here. It's in Greece. It means thoughts to oneself. It's from a guy who has the same name as I had, Marcus Aurelius, and he was writing this book about what today we call philosophy. At that time, it was just his thought to himself. So this presentation will be mostly like this. There are some ideas that I was that are my own. How do I see this karst morphology and potential links with surface karst morphology and cave morphology, speleogenesis a bit. And last week I was in the field with Nenad Buziak. I'm not sure if Nenad is somewhere here. And this lecture is somehow, there it is. It's a bit of a continuation of his talk that he had yesterday, the last talk on cave climate, because we were discussing how to present. And then we decided that the best idea would be to present the talk yesterday that he had on cave climate and today's talk as really taking to heart the idea of a Karstological school. So there is nothing new, there is nothing important, it's just a short overview of development of some basic ideas in karst geomorphology. So yeah, I hope it will give some useful information. So again, this is, as I said, personal thoughts. It's just a self-assurance, If somebody says something, it's my personal thoughts. It's my personal. Okay, so initially I started with this, so I got some ideas about, the development of ideas in geomorphology, and this is from a book by Gregory Levin, and it starts in 1674, and you can see here every entry is just one of these novel ideas in geomorphology. So if initially I wanted to give something more exhaustive, I decided it would be quite long and then no lunch today. So I will focus only a couple of key moments, and just to use this slide, I put here this, the first use of the word geomorphology, sometimes in the 1858, when it was appeared in German literature. And then all hell broke loose with the use of it. You can see that it was continuous development. Good, so let's skip, because geomorphology is quite long. I will use two main ideas from the general field of geomorphology and then see how they fit in this specific type of karst geomorphology. So we should start from the beginning, from the real beginning, and then there is a couple of let's say models that at the time they were developed, they worked quite well. And this is the first model that we have. And if you think about it, and if you put it in a wider perspective, then, and you think only this in the beginning and created, things are okay. So for that time, this model worked perfectly and explained the world. So if you think only of this point, then this model perfectly explains our world and then continuously everything on it. But if you go further, just one microsecond away from this really beginning, then things, as you can see, the naked truth here are somehow more complex. So this model breaks down. It doesn't work anymore. So it only works if you think from the very beginning. And I would like to use this example just to give an idea of how I see this thing of models. So as long as you think of it like, how to say it, like an explanation for the moment, for the time being, then it is okay. However, when you start going into dogma, then things break down, and then you end in something like this, you know, the hell of Dante. And this is true also for us, because sometimes if you don't agree with everything that being said, you can end up somewhere. I'm sorry to inform you that based on the review, your manuscript has been declined for publication. What I want to emphasize here is that a model is good as long as it starts a discussion, and it is not very good if you think about it as a, doesn't work. Yes. It's not dogmatic and it's used for the advancement of our understanding. So that's why I put these two examples with you know, the creation and then what is happening afterwards. So if you use any model, whatever model as a starting point, like this one, then it is okay. As long as we transform this model of evolution of landscape or whatever model in something that is fixed and it cannot be changed and everything has to go there, then things start to break down. And then it's not a model anymore. It is just something that we have to say to be all right. So I'm saying this especially for maybe the people starting from the 5th row back, you know, just not to be, if they read or if you read something about a specific model of a specific type of evolution of the surface topography or a cave, you should not take it that this is fixed and I cannot say anything about it. This is where you start, and the idea is to try to test it and to see if it works or not. And exactly this is what was beginning. So this model was good for many millennia, I would say. And then out of it, it emerged the next one, so-called catastrophism. It was dominating in the late 18th, early 19th century. And again, this model was good at that time, because whereas for biology or even hydrology, people were able to see a change. Plants are growing, animals are dying, and so on, or water is flowing, as we know from Valvassor studies in the 17th century. For geomorphology, for the evolution of topography, it was more difficult to see a change. Things were not changing fast enough so that you can see them. So then this model of catastrophism was working quite well. It was, it didn't start as a model to explain the evolution of everything, but as evolution of animals by Baron Cuvier. However, William Buckland take it to heart and then try to explain everything in the view of catastrophism. And in parts of the world, this was the dominating model. Everything happens as a catastrophe, as a sudden change. And again, it was working for a short period, or for, if you think of continuous evolution of landscape, as I said, you cannot see it very well because it's quite slow. But if you think of an earthquake or a flood or a volcanic eruption, then it has an abrupt impact on the surface topography, and then you can see it. So this model made perfect sense at this time. However, when they wanted to expand it from a very short event to explain everything, it showed how hollow it is. And then in the 19th century, the next generation of, let's say, models in geomorphology evolved, the so-called uniformitarianism. Okay, Hutton and Lyell, and they had this beautiful insight that the present is the key to the past. Because there was emerging evidence already by Luis Agassiz, for instance, in the Alps, and they could see this change in the topography. They could see the change in the relief. Things were not fixed, and you didn't need something very, very rapid or very abrupt to change it. As somebody put it very nicely, you know, in geomorphology, you started to see muddy waters and rolling stones. So then from these, you could see that things are changing, and then you could have a different model of evolution of the topography. And what is important that the same James Hutton observed for the first time that the role of carbonic acid in the dissolution of limestone. So this is a very slow process, and yet he was able to understand it, maybe not directly by seeing it, but by out of the chemistry. And this is the moment when people started to think more about the dynamics of karst relief. And things were slowly accumulating in the 19th century, towards the end of the century, and coming on the heels of Charles Darwin, we have the next big step, the next big advancement in understanding karst topography and karst topography at the end of the 19th century. And this is with the work of William Morris Davis. So at that time, most of the work was still focused on surface morphology, not necessarily specific to karst, but started as the explanation of the topography. And it's interesting that at the end of 19th century, beginning of 20th century, people were more interested in what is happening in the underground than on the surface in terms of topography. And it was the work of William Morris Davis, who sometimes towards the end of the 19th century, in 1890s, came up with the model of his evolution of topography, the classical cyclic model. And this was a model that was somehow at that time combining the catastrophism with the uniformity and evolution in terms of you have a sudden uplift of territory, of a land, and then you have a continuous evolution of it. So he was seeing it in a kind of steps without not as a continuous evolution. And this was used by Grund already in 1914 to come up with this evolution of the karst surface, from a uplifted territory, slow downward erosion, formation of a plain at that time called a peneplain for William Morris Davis. And you can see how these ideas of William Morris Davis were spreading in Europe, because at the time, just before Grund's work, he was visiting the Adriatic karst in Europe with Albrecht Penck, and Albrecht Penck had a brilliant student at the time, Johann Zweig. So the ideas of William Morris Davis, as you can see in his correspondence with Albrecht Penck, slowly crept into the work of Johann Zweig. What is interesting is that at that time, Johann Zweig's work in the karst phenomenon, it was not necessarily one that would take the work of William Morris Davis like ad literam. So he was not interested at that time to explain the evolution of limestone. In his first work in 1899, which came out, I think, 1 year after the visit of Davis in Europe, he was only discussing surface topography. So he was not presenting a general model of evolution. And then he was a student of Albrecht Penck, and the Davis ideas very likely got into his work. But he started with this explanation, and maybe this is one of his important insights at that time about the distinction between hollow karst and narrow karst. And this view dominated for several decades, and it only started to change sometimes in the 60s when Roglic came with the idea of fluvial karst. Already in Zweig, in his later work, started to differentiate between hollow karst, narrow karst, and the intermediate karst, but it was the work of Roglic in 1960s that clearly showed this, the existence of the fluvial karst and the fact that you cannot really separate completely fluvial karst or fluvial processes of karst processes. Depending on the scale you are working on, from really micro scale like millimeter or even smaller scale and going to large scale, you can see that there is maybe a continuum both in space and time that can, so fluvial processes, when I say fluvial processes, I mean normal erosion in areas without karst, are slowly moving towards karst. So it's not a clear differentiation between the two. This is fluvial, this is karst. At the heart, maybe in the area where there's only hollow karst, you can say that at one moment in the time, this is so the overall shape of the topography or the overall shape of the karst, it is a, I would say, typical karst, so it's not fluvial. But then if you think a bit on a longer time scale, then you can see that there are processes, fluvial processes or normal erosion that are also getting into the karst. So just think of the discussion yesterday evening about what is karst. So it's very, I would say that it is very, very difficult to totally separate the two worlds. And I think that the work of Roglic in the 60s started maybe this shift towards not totally separate these two worlds. Okay, so this work of Zweig, so he started in 1899 in his PhD thesis, and it continued to work for another maybe 20 years until his next paper in 1918. But before that paper came out, we have the son of Albert Penck, Walter Penck, who was maybe he could have been maybe a better geomorphologist than Walter Penck, his father. What is interesting, what is important, and Walter came up with a totally, completely different idea of surface evolution. So opposite to what Penck was saying about the evolution of topography and the geomorphology in one cycle from uplift and then continuous erosion down to a level and then uplift again and then continuous erosion, Walter Penck came up with the idea of continuous evolution that is shaped, that is continuously shaped, and this continuous shaping is happening because of the uplift rate. So he was saying that the evolution of topography is related to the rate of uplift. So it is a continuous process. So opposite to the work of William Morris Davis, who was seeing the evolution of topography in stages and cycles, Walter Penck had a view that was more continuous, and it was influenced by the beginning by the rate of uplift. It can be fast or slow, or it could change in time. So it was an idea that I think it was cut short by his very short life, so he died when he was 35. And then it's interesting that the work of William Morris Davis and his cyclic evolution of karst is still used today. It is not valid, but it's still one of the main drivers of studying the surface topography. Whereas the ideas of Walter Penck, they are used in geomorphology, but they didn't made it to the karst with the same strength as Davis ideas. And I think should he have lived longer, it would have been maybe better ideas. But again, his this work of the work of Davis. So he had this first work in the 90s, in the early 1890s, and then towards the end of his life, he wanted to expand this cyclic evolution of relief to karst. So he published one of his finest papers in 1933 about the genesis of caves. And then this was dominating for many years. What is so this work of Davis then came out of the blue. That was at the same time, it was a general direction of research. So it was already Grund in 1914 who developed one of the first ideas of cyclic evolution of topography. So William Morris Davis, while it is not sure whether he did it independently or he somehow knew about the work of Grund at that time. So he had a model of cave formation, again, specific for his view of how topography forms. Uplift and then cave formation underground. Okay. Wasn't me. Okay, it's interesting that in the same paper he introduced these terms, dripstone, flowstone, rimstone, just as a note, so that because we use these words and it's not sure, we don't know exactly when they're coming. So I was surprised to learn that it was his work that came up with these papers. And yeah, because this was at that time so when he wrote the paper and he came up with this idea of cyclic evolution of topography, he was building on the work of Grund 1914. And this work of Grund 1914 was a follow-up of the general discussions that were happening at that time in the field of hydrology and morphology and karst hydrology, and that is the problem of the karst water, which doesn't exist, as Philippe tells us, the karst water table. So there were these two main ideas, whether there is a karst water table or not, or whether there is a karst water or not. And this distinction between the work of Grund and Katzer has been dominated our work on caves and karst for the last 100 years or so. I will not go into the detail of it. We all know about it, so we know, but it was a very important early distinction between these two views. And if you think of the evolution of speleogenetic models, they are all concentrated around the question where do exactly cave forms, above, below, at the water table, how much of the genesis below, how important it is below, how important it is above. And this is a continuous debate, is an ongoing debate, and I will not go into the details of it because I guess today's talk will discuss it in more detail. What is interesting is that at, again, the same time when he had this distinction between Grund and Katzer, Swish came up with his second most important paper in 1918, and he introduced this figure with a dry zone, a transitional zone, and a saturated zone. So this has been around for more than 100 years, and it is maybe the distinction that is the one that is still dominates today. Interesting is that Zwisch did not make the next step of trying to see exactly how he could use this distinction between the three types of zone, the dry, the transition, and the saturated, and important with permanently circulating water, to explain the evolution of caves or the topography. He was still using the model of William Morris Davis, and you can see the same model of cyclic evolution from top to bottom. Because this is something that he was working on for many decades, so he couldn't use the information or the data that Alfred Penck was putting forward about the continuous evolution of the topography. So yes, this is the slide that is the only slide that has to do with speleogenesis. I guess the next 10 presentations will go into the detail of it, exactly where caves form in relation to the presence of the water table and the zones in karst. And then I'm towards the end of my presentation, because I'm mostly focused on surface topography and not on cave speleogenesis. I will continue with some questions. Again, these are questions for myself. So the general view is that it's not that it is accepted, it is just that it dominates. The discussion is this model that was developed around 100 years ago by Grund and then continued by Davis. So is there another model? Should we look for another model? Should we develop a model that goes more into a continuous evolution? Is it necessary for karst, or is it even possible for karst to do it only for surface? Or we cannot do it to understand the surface evolution without getting down into the caves and link the two of them? And then that would be the second. And I have this beautiful image from one of the field trips where you have these different levels of caves, and then basically what I want to suggest or say here is that contrary to surface topography, it is the underground evolution of karst, or the underground more speleogenesis and the underground processes that are maybe also more important for the explanation of what is happening in the surface than what is happening, than only considering the surface topography. So if you want to go for something like surface evolution of karst, maybe first would be to look in the underground. And there has been work here in Slovenia by Nadia and colleagues and so about this, the oldness of the karst and how it's part of a continuum that maybe can be related to the initial work of Penck, of Alfred Penck, the son of Walter. And then the second, because it's about model, can we have a generalized model, and should we have one? And I will skip quickly to the next one. And I'm not sure, because as you have seen, and we will see today, there are numerous models, and not all of them work in different areas. So if you remember yesterday's first talk, the Francis talk, I would think that maybe more important would be first order laws and mechanisms. And to think of these, not to try to put them into a generalized model that would explain everything, but build conceptual models for testing only, and basically have these first order laws and mechanism as a kind of toolbox that you can mix and match. So depending on what you see in your cave, in your study area, in your topography, then you can apply one or other of these. And these are the ones that should be, the very useful one, or the very, the very strict ones that should guide our work generally, not an overarching model that explains everything, and that, of course, it doesn't explain everything, and it can be changed. It can be changed, and it should be changed, and it will be changed, but because it's the larger it is and the more overarching tries to be, it is the more difficult to change it, because there is going to be always some, but it works there, it works there, it doesn't work there, and so on. Whereas the first order laws and the mechanisms, these are fixed. You cannot work with them. It's like when you go caving, if you have a lot of tools, and you choose the one that is suitable for you. You don't have to put everything on you. It's just the things that are working for that specific cave or for that specific area. So yeah, that would be my last slide and my last words today. Oh, I have 5 minutes. Good, thank you.
You just did what I wanted. Yeah, thank you very much.
Been in time, you mean?
Yes, and in time, thank you very much. That was great. And especially because, yeah, it is important that we decide what we want to have in the future, the global model, but it can't be done, actually. Yeah, thank you very much. So if there are some questions, please, or remarks.
Thank you very much for that very enjoyable overview. One thing you did not mention is climate. And there's all seemed to me to be strange that cave evolution seems to go on regardless of the climate in much the same way no matter where you are, except for the extreme ends like permafrost. So we can have a subterranean model for karst, almost universal, for caves in karst, almost universal. But the surface topography is very dependent on the climate. And there have been attempts to make models for humid tropical karst and for temperate karst. And Grun's model is somehow a compromise between the temperate and the tropical. Would you like to comment?
Yeah, I wanted to go into this, but then the way I see it, again, I see it as a continuum. So we have a surface topography in parts of Romania where I work, which really much looks like tropical karst. So very likely that developed, it's not maybe tropical, but close to it. So it seems that that developed in the Miocene. But then we don't know exactly the age of it, but based on the morphology, this relict conical karst, it looks like it. And yet in this tropical karst, we have the present day temperate karst. And then I'm not sure if I don't see it because it doesn't exist, or I don't see it because I cannot see it yet, or so, or it does. I see it again like a continuum. So it was not that it had we had tropical karst and then it all of a sudden changed to a temperate karst, but it was a slow and gradual change at the surface that was shifting from tropical to temperate. It's also present here in Slovenia, where there are caves that have sediments that are in excess of 5 million years. So again, it's before the Pliocene. And the topography on the surface, the present day topography, it's a mix of, it's an inheritage of that tropical and the present day, the temperate one. But I'm not sure, and that's why I didn't want to discuss too much about it. In my view, it's a continuum, so it's not a separation. So whereas for a specific moment in time, we can see that this is karst, this is tropical karst, this is glacier karst, and this is temperate karst. If I take a step back and I look at the present day topography in that area, I cannot say that this is only the result of temperate processes only, like here in Slovenia, the surface topography around us. I see it as a combination of tropical karst slowly changing into temperate karst. So this is, again, this would be my personal view of, again, if you take timestamps, then you can separate them. If you want to go into the detail how this specific topography changed or developed, then it's the result of both, or since the area was uplifted. And then it was a continuous evolution of it.
Yeah, thank you. I also think that the time is crucial because you passes from different climates and from different tectonic movements. So it's really crucial for the surface. And what you get, it is climate in different time. So time is really one. Some other comment or question, please? We have some minutes more. Okay, if not, thank you very much, and we can discuss later during the coffee break with him. And now I ask Ugo Zauro to continue with glacial karst morphology.
I present a case of karst and glacial evolution of an area of Monti Lessini in Veneta pre-Alps. The next. The aim of this study is to understand the possible role of a karst process in the evolution of some form of glacial deposits. In the first place, it must be stated that any polygenetic form in glacial environment of the past must always be considered in the context of the relative glacial system, given by a complex of form of erosion and form of glacial deposits. Next. I have. Let us now see the glacial system taken into consideration, identified starting from the most evident glacial forms, resulting from the local glaciation of a plateau area. It is the old glacial system of Vallon del Malera, called with this name, in the Lessini Veronesi Mountains. The Lessini, the area is just out on the right side, but you see a part of the Lessini Mountains, the large glacial system of Adige and Garda Lake, after Abbe. The Lessini Mountains here, and the area where there is this glacial system. In first place, it's possible to recognize a U-shaped glacial valley, glacial trough, the most typical glacial forms of central western Lessini Mountains. You see this glacial trough. And this form, you see, beside, to the north of Lessini, there is the Dolomitic group of Carrega Mountains, 2,255 meters, and the Vallon del Malera is, you see, to the right side. At first glance, it seems to be an oversized glacial form compared with its orographic and altimetric context. In fact, it could derive from a wider glacial system, which in ancient times had its beginning from the glacial cirque of Malga Posta in Carrega group. You see here that this glacial trough in the lower part of the imagine and the glacial cirque of Malga Posta. There is a very deep incision, Val dei Ronchi, separating these two forms, which in our opinion were connected. We don't know when, but we will see something now. The glacial Vallon glacial system continues in the Squaranto Valley, where there are extensive morainic covers and also forms of erosion, standing out among these is a large rock terrace, which may have been shaped by the ancient glacial Tonghi, when it is dead in the Carrega group. You see, to the left there is the Vallon del Malera. Instead, you see the upper part of the Squaranto Valley, and this, perhaps is this rock-cut terrace here. Here there are a lot of moraines, bottom moraines especially, but probably deposited in more phases of development of a local glacier. You see better here the part of the Vallon glacial trough, upper part of the Squaranto Valley, this kind of rock cut terrace. This is the recent incision of the valley. This is the terrace. We have some particular relief you will see now also here. This is probably an old lateral moraine. We will observe a ridge located in the first moment, located on the left side of the upper Valle di Squaranto, which immediately suggests to be a lateral moraine of the Vallon glacial system. However, it is noticeable that this ridge is predominantly in rock, and that very little of glacial till remains. In reality, in addition to a few calcareous diamicton, there are quite ancient soils that contain flint tools of the Valois types, witness of ancient human frequentation of the area. You see here this ridge in a leader model. This ridge, the north is to the right now, and it is not connected with the thick morainic cover which is here. You see on the field the same form here. This is the upper part of the Squaranto Valley. This ridge here is mostly composed by limestone. There is very few of moraine of till deposits above. Details of this form. Carren inside this form, in the front especially part of these forms. Red type soils inside the form. The upper part of the ridge is here, this here, and here you see red soils with remains of the till deposit. Inside these red soils we have found the Valois type flints, human artifacts. This shape could be explained by the fact that at first time morainic ridge was several meters thick, but later the karst solution processes consumed the moraine. On the other hand, the latter protected the underlying rock in which the solution processes led to an average lowering of the moraine bedrock interface lesser than that which would have occurred if the moraine cover did not exist. An attempt to schematize this phenomena, morainic ridge, consumption of diamicton by solution, or especially by solution, development of carren, and remain the form. Returning to the shape of the ridge, it is obvious that it cannot be defined as a morainic ridge, since it is mainly made up of massive limestone in place. The only possible interpretation is that this shape is the result of a particular process of over-imprinting of a moraine on the underlying limestone rock. It is therefore proposed to give this shape the name rock ridge from a morainic ridge over-imprinting, or the shorter one of over-imprinted ridge. Here we have one other dam, leader dam, and the Vallon del Malheur, the northeast to the right. The Vallon del Malheur is used here. This is the upper part of the Squaranto Valley, the large rock-cut terrace. And here is possible to recognize two rock ridges which could, if you consider the glacial system, could be part of the old morainic amphitheater of this glacial tongue. If you go to see this with two rocky ridges, we will discover something. You will see in more detail where you have already seen this rock, this ridge, these two ridges, north with up, two ridges here, which are covered by a dense forest. You see how these ridges are ruiniforms with toppling phenomena and so on, and deeply calcified, very deeply calcified, because this limestone in normal condition is massive. Here are very deeply calcified. And so, in my opinion, they are very old remains of a very the result of imprinting of very old morainic ridges on the limestone below the ridge. You see also here strong calcification of these forms. And I want just to remember when in June 2010 we have a field trip in the Dinaric karst. I've seen some forms that perhaps could be similar for some aspects. This is a large polye, but you see, for example, some forms who could be studied better. I will only see this could be for some aspects. You see here, for example, the remains of the imprinted ridges deriving from a morainic arch, old morainic arch. Also here, I think it's not easy in any way to understand exactly these forms, but for me they can fit with the system, glacial systems, and be derived by the imprinting of morainic ridges. Thank you, I have finished.
Ugo, thank you very much. Is there some comment or question, please? Okay, Derek.
As you know, Hugo, we have a lot of glaciated limestone in Canada too, and it's my experience that if there is more than about 1 meter to 1.5 meters of moraine with limestone clasts in it, the bedrock surface underneath will be undamaged by dissolution. We find glacial striations perfectly preserved underneath 1 meter of clast-rich, limestone clast-rich till.
Yes. Thank you.
Thank you. Some other comment? Stan-Erik?
Thank you, Hugo. This was very interesting. I think this idea of superimposing or imprinting is interesting and real. And it reminds me about something that Paolo Forti presented some years ago, that he had some ridges which had caves inside them because he thought that the cave roof was cemented and hardened by the process of speleothem formation. So through continuous karstification, the ridges which contained the caves were standing proud. So that would be imprinting from below, whilst you have documented imprinting from above.
Above, yes.
I think that's an interesting idea.
Yes, it could be interesting, yes.
Thank you.
But anyway, the problem is the old remains of glacial system, all the glacial system are not easy to understand and to be dated. But if we consider the different part of the system, and if this part fit with the general model of a glacial system, it's possible for me to begin to study better these forms.
Okay, thank you, Zauro, very much for this nice presentation. And we will continue with the next one by Elena Gezert and Josef Szupinski about the identification of karst depression based on LiDAR. Please, Elena.
Thank you very much. So we are going now to the area of the Slovak karst region, which is the, like you see on the picture, the typical or classical karst of the Slovakia in the more moderate climate zone. I'm responsible in this project for the geomorphology, and my colleague who is not here is responsible for this GIS stuff. So I hope I can explain it enough good for you. So for these which are not familiar with the geography of the Slovakia, the Slovak karst is situated in this square. So it is a transborder region to Hungary, called also Slovak karst, Aktale karst region. And it consists of different plateaus, regions, which are divided by deep gorges, like here. In the eastern part, you see typical plateaus with the planation surface and very steep slopes. We have also like canyon-like parts of the Slovak karst. And this everything brings us a very classical geomorphology of the karst with a very good developed surface and also the underground. From the geological point of view, here's the eastern part of the Slovak karst. This color means Wetterstein limestone, so very good quality limestones. On the ridges of the karst, we see some sediments which are from the Pontic age, which are covering the old planation surface. Yes. That's the LiDAR. We were waiting very long time for the LiDAR. We started to do with this topic maybe 10 years ago, and we had own small LiDAR to scan small parts. But now at the end of the 2022, finally, we've got LiDAR which is free accessible for all in Slovakia, and now we can start to work with this. This is the western part. I will not speak today about the character of the karst depressions in the Slovak karst, because they are really huge differences. If you are talking about the western part where we are now, or eastern part, which I'm going to present you a little bit further, you see it's very good developed. The density in this part is around 70 dolines per square kilometers, but the eastern part it's only around 10 to 15, and this is also some difference in the evolution in the past. So we decided to choose this plateau like a research area for this purpose for the presentation now. You see it's completely different, like this. I'm going back. So it's slightly inclinated to the southeast, and because of this also formed dolines or formed karst depressions has this direction, this inclination, and they are also with the longitudinal axis developed to this side. And some of them are not very good recognizable. For example, in these parts we have some which are only like of 2 ridges or maybe 3 of them. Some parts like this here we are not sure what's this it. And we started to do this like geomorphological work many years ago by field mapping, classical field mapping, maybe 20 years ago, when we had only topographical maps. A few dolines were inside. After that, we were going through the morphometric analysis after the methodics of Ugo Sauro from 1993. And now we are starting, or we would like to know something more about this area by this LiDAR mapping. So it's not so easy for us. I need to tell that the LiDAR is for us not the purpose. It's for us a help, little bit, to understand and to have a better overview about the area. Maybe you can turn on the video. So because the situation is very complicated, we have the fault you see in the middle, which is divided the eastern part of the Slovak karst into two hydrogeological parts. We have very different forms. Some of them are funnel-like, some of them, or the most of them, not. But we have also a lot of geomorphological forms like lime pits, for example, and small quarries, which are in the area situated. And because of this, it's not possible to analyze these dolines only from the LiDAR, but it's necessary to go to the field and have a look what's this. So this was our work in 2003, only to think about it, 20 years ago. After the geomorphological mapping in 2011, we had a few of the lines which we can found in the field. We done this morphometrical analysis. Yeah, and the reality is now here. What we would like to have like a help in the next analysis. We started with a colleague from the GIS to work on the deep learning of this model. So we have this free accessible data from laser scanning. These are with the resolution of 1 meter, but the accuracy is 10 centimeters, which is registered to the points. We prepared some models which were analyzed, and we started to do some model training because we wanted to have the overview what this everything is. So you see there are some dolines, they are heading direction of some fault-like valleys which are dry in the part. But we have also some of these, like these points, and we were not sure what's this. We are still not sure in some parts what this, but we made the geomorphological mapping now in the region. We know that man-made quarries, which were used like limestone for lime pits, so burning lime. We have in the area of this one only plateau more than 800 of these lime pits, and we tried to smooth the relief in this region so that they are falling out from the analysis. So this is like an overview on the LiDAR, on the dolines. Maybe you can see with your eyes some of them are missing, so we are thinking still about this. We need to go for the field mapping. What's this, for example, or how to deal with these forms. That's not polyas, that's not real uvalas or something like this, but the bigger depression. This is around 1 kilometer with more smaller dolines which are on the round of these forms. Or something like this. Is this one doline or it's 3 dolines? It's not easy to have a look. What we analyzed, we made many layers which we tested. This which we are using now. It's a hillshade and slope with the accuracy of 91% of the dolines which are automatically analyzed. But we analyzed more than 1,000 dolines, and the next 200 were drawn by hand after the geomorphological mapping or studying the map. So another layers were not enough for us, are not accurate. And we used also different models, which you maybe know from this GIS analysis. But okay, now it's working. Yes, what we learned. It's like it was said a few minutes ago that different karst areas are different in the geomorphology, in the development, and so on. So we know some another analysis also from Slovenia, from Andrej Mihajlović, The models which were used by different authors are also different because you have different geomorphology of the area. For our dolines in the eastern part, it's the best to use the square, which is 512 to 512 meters. It's because we have quite big dolines which are not so good visible, but if you have the square, it could be cut it and divide the line automatically by this deep learning into two different dolines, but it's one. So we made these squares bigger for this purpose. What's going on these typical cone forms, but it's not too much, like you see. These were analyzed very good with the accuracy of 100%. We had problems with the asymmetrical dolines, so we needed to do it manually. And also with the dolines which are in the lines, like you can see here, because this was, the deep learning was working like this is one doline, but you see there are more of them, they have rims which are maybe not so good visible for the GIS. We made 60 runnings, epochs of this, but after 58 there were not visible changes in analysis of these dolines, so we stopped this on the number 58. And yes, it should be verified in the field, it's clear. We made a lot of this stuff before the deep learning, but also after this. Another thing which I mentioned are these lime pits. You see small holes. They are still around 2 to 3 meters big in the diameter and 2 meters deep. But they have very good visible rim, so it was quite easy to filter them out from the model. So in our analysis, it's not this form, which is anthropogenical form of the karst included. Yes, so this is what the computer made, and this is after the analyzing of us by hand. You see some of the lines are a little bit corrected. So we decided some of these automatical dolines not include in the model, but some of them we drawn by our hands from the analysis. And this is like an overview. It's not very important. It's only for this plateau, for this testing area. So we made almost 1,200 dolines. In the whole Slovak area, karst, which is already done, is around 8,000 of these dolines. These are, if you are going to the average or mean numbers in the depth in the axis, or are very similar to this, for example, which are average in the Slovenia analysis of Andrej Mihajlović, for example. The orientation is from west to the east, or from the northwest to the southeast, like I told, because of the general inclination of the whole area. That's the main point of the work. So what's next? For sure, it's only help for some next work. Yeah, we are working, or we want to work until the end of the year by the analysis of the whole Slovak karst area. We made also now some different statistical analysis, which I'm not presenting here, but like in the slope aspect geological settings of the dolines, the most of the dolines are developed in the Wetterstein conditions, like I told. The bottom of the elevation of the bottom, which are helping us to reconstruct the paleo valleys, the old valleys, which are visible also here on this model, or here you can see. And to explain a little bit better on further geomorphological situation. Also in the local area of the Slovak karst, we have really different development in the western part and versus to the eastern part, so we hope it will help us. By the end, I need to tell only one sentence from my teacher of the geomorphology from the university. who told that the relief is not virtual entity but a reality. So we are still thinking about it, and we want to use it like help for the next analysis. Thank you very much for your attention.
Thank you, Elena, very much for your presentation of your work, but unfortunately you spent all your time, so please take the questions or remarks to her during the coffee break. Thank you very much, Elena. And now we move to the next presentation by Uros Tepišnik, and we go to the Ponor karst.
Hello, my name is Uros Tepišnik from Department of Geography, University of Ljubljana, and I'm about to present multi-phase development of Ponor type of contact karst on Zrem Plateau. This is an area in Istria, northern Istria, situated in Croatia. And before I start to talk about a case study of this Ponor contact karst, I would like to discuss a bit of history about contact karst or Ponor type of contact karst. And actually, if we are talking about Ponor type of contact karst, it's a geomorphological environment, which is quite specific. When we have fluvial system, so inflow from fluvial system, streams are flowing towards karst, and on the contact with karst, they are sinking into the karst, forming specific landforms, like blind valleys, if they're long enough, or Ponor steep heads, if they're short kind of features. We have specific type of speleology, so lots of paragenesis is happening on the contact karst, and also, of course, groups of collapsed lines, and also the longest sections of roofless caves are usually present on that kind of Ponor type of contact karst, because we have horizontal cave systems and also flattened area in the vicinity of contact. And this contact karst was studied in Slovenia probably from 50s, 60s, started with Ivan Gams, continued with Gospodaric. And the most detailed study about contact karst was done by Professor Mihevc. He mapped all the contact karsts in Slovenia and made some conclusions. And after his research, probably, maybe I'm exaggerating a bit, but hundreds of articles about contact karst were written. And, but even though we have lots of literature about this, we don't have some specific pattern which would describe connection between specific morphologic features which are typical for some kind of geologic settings, hydrologic settings, or maybe topographic settings of the area. So we just have lots of case studies from various areas. And my study area, which I'm about to present, is Zrem Plateau. Zrem Plateau is situated somehow on the border. Actually, it's in Croatia, close to the Slovenian border, actually, and it is stretching. This is some kind of corrosional plain. It is stretching from the sea towards the canyon of Mirna, somewhere here, and it's some 5 kilometers wide and maybe, I would say, 40 kilometers long, corrosional plain, completely dissected by the lines, a couple of collapsed lines we also have here, and maybe some very not distinct conical hills and uvalas, but more or less this is karstic plateau, it means corrosional plain. And from northern part and southern part, it is engulfed by flysch areas from where streams are flowing towards Zrem Plateau and submerging on the contact. So we have from northern side and from southern side, we have developed that kind of environment which we are referring as contact karst. And even though this Zrem Plateau, Istra, is part of classical karst, it was never studied from a geomorphologic point of view. It was completely overlooked, so we just don't have any literature about this, except geologic literature is existing about this. Hydrology was done here, but no one was studying geomorphology in this part so far. So if we are, okay, this is geology. If we just have a brief look in geological and hydrological features of this area, so the rim plateau is basically some kind of anticline, which is of course flattened. This is plateau. And from the northern part and southern part, we have slightly elevated topography where flysch bedrock is presented. And contact in between flysch and carbonates is normal on the western side, and on the northeastern side we have reverse fault, and also the whole southern section is also reverse fault, represent the contact in between flysch and carbonates. And water which are discharging into karst from northern side and southern side are running in the subsurface towards the spring Bulash, which is in the canyon of Mirna in the eastern part of the study area. So if you look just a couple of pictures, this flat area, 5 kilometer wide, is the rim plateau. It is more or less flattened, completely covered with this Mediterranean vegetation, except where it's cultivated. And waters which are coming into karst are submerging in the subsurface in various kind of ponors, sinks and stuff. Maybe the most nice looking is Ponor Butori, when we have small collapsed line, and this stream is then sinking within collapsed line, so this is the picture. And all waters which are running in the subsurface are emerging in the eastern part in this spring, which is now used as a pumping station for water for northern part of Istra. So what kind of analysis we did here? Just basic geomorphological approach, because as it should be. So we started with morphographic mapping of the area. Since there is no LiDAR data for Croatia available yet, we were using all military maps and then normal geomorphological mapping, like zigzagging through the bush and trying to get as many geomorphological features as possible. Morphostructural data we acquired from geological literature and maps, and morphometric analysis was done more or less with these topographic maps which were provided. And according to geomorphologic mapping, and we tried to establish some kind of morphogenesis of the whole area and morphodynamic interpretation. So when we mapped the whole area, we actually discovered a pattern, which I will describe now in 3 different sections. So northwestern section of this rim plateau is acting in some way, northeastern section in another way, and southern section I will present on the end. So it's like this, that it's not working yet. Naprej, prosim. Eno nazaj. Okay, this is northwestern section of this rim plateau, and here is the contact between flysch and carbonates, and this contact is normal. So we have Cretaceous limestone dipping below superimposed flysch, which is overlying limestone. The dip of strata is about 20-25 degrees. And we have fairly big water courses coming into karst, and they're forming some kind of blind valleys. Blind valleys are somehow elongated in some direction, and those blind valleys are quite distinct in a ground plane, but if you look at them on the field, they have very gentle slopes, fairly visible on the surface, but we have sediment cover, and we can distinguish between active part of blind valleys and relict ones, so non-active, still covered with alluvium, but they are actually not functioning. They don't have hydrologic function anymore. And if you look at their orientation, there is some kind of merging together, all these blind valleys, and on the end, they're continuing in some elongated depression, which resembles to a valley. Actually, it's like dry or relict canyon, which is actually orientated towards west, and it's crossing the whole rim plateau. The same situation is this blind valley, Sterna. It has active and relict part of blind valley and canyon in the hinterland, but only one stream we have on the north, which is actually entrenched into carbonates, forming very narrow and deep canyon, discharging in Dragonia River. Here we can see an example. This is a blind valley with no distinct final part. Usually on the blind valley we have some slope on the end or something like this. This is very gentle, like half a meter or maybe a meter higher. And actually this blind valley is continuing in non-distinct valley or a canyon towards south. If you look at the northeastern sector, we have different geologic contact here. Here is a reverse fault, not normal contact, but reverse fault. And along this reverse fault, we have also some quite big streams which are coming towards the contact, but they are not forming blind valleys. Actually, we have only Ponor steep heads. This is just some short sections which are entrenched into karst, and they are quite steep, with steep slopes. They're not gentle as earlier, and water is submerging within ponors or sinks within these forms. And in the continuation of each of these Ponor steep head, we have like dry valleys or relict canyons in the continuation. And everything looks like this, quite steep slopes, and below these slopes we have ponors or sinks and features like this. And we can see from drone view quite distinct slopes around end of Ponor steephead. Contact is very close somewhere here, and some in continuation we have this dry valley which is Relict Canyon. And southern section is also along the normal fault, which but the streams in the hinterland are very small. These are just small erosion gullies which are bringing water to the contact, and this contact is along this contact we have plenty of Ponor steepheads actually discharging these small streams when they appear actually on the surface. They have quite steep slope towards karst, but they are somehow interconnected in between. We have some lowland connecting all these Ponor steepheads into one elongated depression. It looks like this. So elongated depressions along the steepheads, ponors inside, but usually it's dry because there are really small streams coming into these depressions. And according to this data and also additional data which we did on the fieldwork, we actually managed to establish three-phase morphogenesis of the area. So basically, if we have corrosional plane, it should be formed in some base level. And in the base level, where rivers from the Flysch were flowing on the surface across this base level corrosional plane, crossing, and hydrology was actually established somehow according to the dry valleys or dry canyons which we managed to map. And this phase one was actually phase which we refer as shallow karst phase, so in base level. Okay, and after this uplift came, so water table drop, and those rivers were entrenched into small canyons, forming features which we saw earlier. And later, in the present phase, which is third phase, actually decoupling happened. So majority of the rivers actually migrated to the subsurface, forming blind valleys along the contact, which is normal, Ponor steepheads along the fault line contacts, and all the rivers were actually put into the subsurface except Dragonia and Pogania, which is still in the canyons and well visible on the surface. So during our study, we actually established this multi-phase evolution of contact karst, and also something else is quite visible from this. Some kind of pattern. We have specific hydrologic and geologic settings, and along these settings, we actually managed to discover that there is a pattern between geology, hydrology, and the landforms which will form. Along the fault lines, we have Ponor steepheads. Along the normal contacts, we have blind valleys. And this knowledge can be, from now on, successfully applied to the other regions of contact karst in Slovenia, Croatia, or wherever, and try to reinterpret them with this knowledge which we have from here. Thank you.
Thank you, Uroš. So you think that is that related to the regional uplift regarding counterclockwise rotation of Adria plate in the last 6 million years, yes?
Yes.
Like we dated with Andrei in Blind Valleys in Matarsko Podolje.
Yeah, probably something like this. I was
Okay.
discussing this with people who are dealing with tectonics, and time frame would be something Pliocene or something like this, or even earlier, but they're not sure. So this is probably discussion for the next year.
Okay. Yeah, and discussion today afternoon where we will discuss very similar situation in our karst plateau closer to Postojna. Thank you, Uroš, and we don't have more time for discussion, sorry, and you can ask him more during the coffee break. And now we will move to the next presentation, please, by Kazmer et al. And they will talk about the uplift recorded by hypogenic karst features. Please.
Ladies and gentlemen, let me introduce the team working in this field. We are 4 geologists. We feel sometimes a bit embarrassed here because we are neither we are very undereducated in both in geomorphology and speleology. So our thinking is sometimes a bit different from what I experience here. That's why it's very instructive for me to spend the second time 3 days in this group. The team is Professor Shafia is from the National University of Malaysia. Rizan Nahar was my student from Sumatra who recently was captured by a Belgian university, and he changed his beautiful tropical field area to the stormy seas of the North Atlantic in Shetland Islands. And Christoph Gajcik is the leader of the expedition, of the Peru expedition, where the travertine results were beautifully introduced to us by Andrzej Teach yesterday. We would like to dedicate this study to the memory of the late Andrzej Klimczuk. His books and papers were very much of an inspiration to us to carry out this work and to understand the feature what we have seen in the field. And it was a very honorable request from him that he asked us to submit a manuscript to the journal Geomorphology for a special issue he wanted to edit. Now, I didn't do my homework, sorry. Yeah, so I love the notion of tectonically stable Thai-Malay Peninsula. It's still an ongoing notion in many publications there, and there is an increasing understanding among researchers worldwide that there is no tectonically stable area anywhere on Earth, be it oceanic or continental plates, orogenic zone, or so-called intraplate regions. Everywhere there is some kind of tectonic. So we went there just to challenge this notion, to find some tectonic activity in the Thai-Malay Peninsula. We went there to study marine notches because they are very, very sensitive recorders of tectonic uplift and subsidence, but instead of, found some, but instead of them, we found larger terrestrial notches or cave notches, a lot of them. So we studied them, we studied the phreatic epiphyte vadose features, and we tried to establish a kind of stratigraphy of these features, so the overlapping, the overprinting succession of these features. And there is some guesses about, I would say educated guesses about the depth of these phreatic processes, and we want to discuss about the Cenozoic uplift. It's a bit later. How did I do it the first time? Okay, the location is the Thai-Malay Peninsula. It's in the center there is a long ridge running up to more than higher than 2 kilometers high, and in the western side there is a alluvial and marine tidal plain, and between them there is obviously there is a fault zone with 700 kilometer long range of hot springs there. These hot springs I will show you some features from there. And this is in the halfway between the capital Kuala Lumpur and the Thai border, the Kinta Valley. This has been the site of tin mining, and that's made the city of Ipoh very rich. The surrounding, most of the region is granite, which has been weathering and it's being eroded, and the alluvial, the rivers coming from the, carry the sand, the alluvial sand to the, I always spell something wrong. Okay, so this is the landscape. These are the background. There is the granite hill, the tin-bearing granite. In the foreground, there are the limestone hill, Permian limestone, which are absolutely full of holes, all kind of karstic holes. Between them, there is the alluvial plains. These rivers sometimes flew through the caves and the well, and there's a lot of lakes are here, the abandoned tin mines. Tin mining, this made Epoch rich for 100 years, and this, when in worldwide, the tin packaging of food was changed to aluminum and plastic packaging, the tin mining collapsed, but Epoch still successfully managed the change. We have visited more than 20 caves in the region, and what do we do? Shit. I'm not yet. Okay, so what do you do when you go to a cave in Malaysia? You find, why did we go? You find, okay, there are millions of caves. How to pick them? We are not cave photographers, so we want caves which are easy to access and which are well illuminated inside. Many of the caves are temples. Temples, Chinese love to put all kinds of temples, Buddhist temples, Taoist temples into the cave. They are very wonderfully maintained, cleaned, easy access, and properly illuminated for photography. Some of the caves are the tourist attractions. There is built a pathway there. Note that this river is flowing through a cave. Previously, this cave was full of tin sand, which was removed carefully by the Chinese diggers to make it. Some of the caves are painted well, like this one. Okay, let's go on this. And but there is left is forward. No. I am sorry, I made such a nice.
It's not working. Just tell everyone to the next slide.
Okay, can you go back one? One more back? Yes, thank you very much. So there are caves, sometimes they are nicely painted, sometimes ugly painted black, so we cannot make photo. The poor communities can only make a ladder there, so my 50-kilogram assistant wanted to climb up. I declined the possibilities because I'm 100 kilo. And on the right, lower right stand, I recommend, this is a wonderful restaurant in a cave, the most beautiful I have ever seen. The hot spring resort, important, hot spring, sulfurous smell of the water. I recommend anyone to go there. You can easily, easily book a bungalow there with private pool from 1,000 euros a night upwards. Next one, please. So this is a nicely painted cave. You see the phreatic features on the roof. There are beautiful niches cutting into each other. In the background, there are niches or scallops, as you say them, and two corridors, two tunnels, one going straight ahead and the left one is going, so that deviating. And everything is a nice concave negative forms typical for the phreatic features. Next one, please. The beautiful scallops. These are the scallops showed us where Lucas planned from the high cold air of cold climate of the Alps were like 2-5 centimeters in diameter. These are 2 meters in diameters. And I invite Lucas to please comment us how to determine the orientation, the direction of the flow in these scallops, by the scallops. Next one, please. Yes. The keels hanging from the roof, they are just half meter to 1 meter, 1 meter. All kind of features are hanging, projecting into the cavity. Next one, also from the top and also laterally from the right. This picture which is like 3 meters, and this is a 1.5 meter long projecting something, I would say, pendant or not. I'm not familiar with the proper word here, just projecting into the cavity. Next one. Yes. There are, these are, the holes are like 0.5 meter to 1 meter in diameter. This is a typical Swiss cheese environment. There are holes in every direction, everywhere, but more or less this could be like a result of horizontal flow of water. Next one, please. So these were the phreatic environments. The epiphreatic produces the typical, the classical notches, which are the terrestrial notches or cave notches. There on the upper left, there you can see one notch, like 1 meter high, but hundreds of meters long. On the upper right, you see 2 notches above each other. In the lower left, you see 1, 2, 3, 4, 5 notches, maybe more, but the concrete floor, so we cannot see all of them. Don't forget that these notches are around large cavities in the lower left, or they're just between these so-called feeder dikes on both sides, more or less tend to be symmetrical. Sometimes it's symmetrical, sometimes not. It was a very nice, distinct study to find something about them. The notch height the notch height probably reflects the oscillation of the water table a long time ago. The depth of the notch, probably the time passed, so how much time is needed, but notch depth is very variable from a few centimeters. The deepest one we found was 1 meter high and 8 meters deep. The cross-section can be round, can be triangular. It's another nice topic, probably for a master thesis. And there are multiple notches, probably the results of repeated tectonic uplift. Next one, please. Yes. So these were the phreatic, the vadose, and here is the Swiss cheese. Nothing missing? Okay. Yeah. So the Swiss cheese, when you find a notch, it develops laterally. It starts somewhere and it's moving right ways, maybe towards the right on this picture, and it cuts everything, destroys everything in its path. If it is going along a Swiss cheese morphology, it just cuts at the bottom and exposes it to us. The notch, you can see the horizontal notch in the background. On the right side, you see that every pendant from the roof, which was originally a Swiss cheese morphology, was cut horizontally below. So this is how the epiphreatic feature just overprinting the phreatic features. Next one, please. This one is, everyone is familiar with, all kinds of vadose, paleothemes, stalactites, stalagmites, flowstones fill up the cavities. You can see the cavities, the beautiful scallops on every, and niches in every side. Next one. Yes, and finally, the cave is filled up by alluvial sediment. This is a usual tin-bearing sand in a cave, filling up by a beautiful notch, totally horizontal on the roof. Next one. Yeah, and then when you see the scallops just openly in the air in a cave, and you see some bacterial erosion growing all there. This is typically subaerial erosion form. Next one. So now I would like to see my story, because I don't know it by heart. So we found phreatic forms which formed at depths. Why 600 meters more, of course? Because the morphology of the hills in the Quinta Valley are up to 600 meters. It could be more, of course. So when you see that at the top you see this phreatic morphology, probably the phreatic morphology below was already still 600 meters depth. There was epiphreatic forms, cutting everything, the notches, and the vadose forms. And when they overprinted each other, it indicates that phreatic, overprinted by epiphreatic, can happen only when everything, all the terrain, all the land is rising, is being uplifted. And it reaches, and finally when it's being epiphreatic, the notches cut everything, and then in the vadose environment, everything is being eroded by the being eroded by rainfall, by rockfall, by collapse, by everything. And this is when we can find a cave and when we can access them. Usual cavers just walking and crawling. The special cavers like the Danish seabed by diving. And these are the caves. But we should know that the caves we are studying and we are admiring and finding all kinds of phreatic features are still being formed underground below our feet. So the earth inside in the karstic region is full of the same cavities, even bigger cavities that we can observe in the mountains, facing us. Yeah. Thank you very much.
Thank you, Kazimir, for a very interesting presentation. We have a question here or a remark.
Thank you for an interesting presentation and also for your international constellation of people. It is a challenge to work in tropical caves. because in the past we have interpreted many of these cupolas and things like that as phreatic water-filled forms. I have been working in Mulu last November, and what is striking there is that most of these features which we think were phreatic are actually results of condensation corrosion going on for a very long time, and you can totally change the impression of the cave over time. So what we found is that scallops and epiphreatic features and things like that are preserved only a few meters above the present water table. When you go something like 10 meters above it, the cave is completely changed by the condensation corrosion. And you showed a few slides where you had these cupolas were intersecting speleothems. And that is a very clear evidence for that condensation corrosion is going on. So I think you have a lot of very interesting features, but it is very dangerous. We have all gone into that trap of interpreting everything as phreatic, but it's not. Thank you.
Okay, thank you very much, but unfortunately we have no time for more questions because we have to go to the next one, so thank you very much again. And we have the presentation by Matej Lipar, and we go from Malaysia to Australia.
Thank you, Nadia. Good day, everyone. This presentation is about a peculiar landform which we discovered when we were studying the karst topography on the Nullarbor Plain that brought together me and my colleague Mateja Ferk from Slovenia, a colleague from University of Ljubljana, and also a colleague from Curtin University in Perth in Australia. And before I continue, I'm just going to acknowledge the paper written by Joe Jennings just 60 years ago, talking about the problems and questions about geomorphology of the Nullarbor Plain. And this paper is still interesting to read because half of these questions still remain. Half of them we hopefully solved, but we also discovered many more questions, of course. And just to put the Nullarbor Plain in a big picture, this is the huge plain down in South Australia that represents one of the largest karst areas in the world. If I actually move onwards, this little thing is Slovenia. So we're actually dealing with a really large landscape. It's extremely flat when you just first time cross it. So this is how it looks. And this is basically how I can actually just show you the simple geology, which is actually formed by 3 different layers of limestone. So the first one, which is white color, is Eocene limestone, then it goes into the Oligocene. And the last one is Miocene limestone. Why we study this landscape, why it's so intriguing for us, is because it's just been uplifted about 14 million years ago and not folded, and nothing really happened to it. So it's basically just standing there, and it represents an archive of 14 million years of geomorphological processes that happened in this area. This is the extremely, extremely exaggerated DEM of the Nullarbor Plain. So otherwise it looks completely flat. And over the 10 years, we did a little bit of geomorphology over there. So I was the one that mapped every single longitudinal dune right on the edges, and they seem to have a phobia of the carbonates down on a plateau. But one of my colleagues at La Trobe University mapped, this is the orange color, all the imprints of the longitudinal dunes that were apparently right on the carbonate, and now we only have the remnants of what they were. These red dots are all the caves or other features like blowholes discovered on the Nullarbor Plain. And the blue dots are the pocket valleys. Me and my colleague Mateja Ferk, Waltz Matilda, all around this escarpment over here in Israelite Plain. And basically every second year we find something new. So today I'm just going to talk about this peculiar dot, the pink one. And it happened because we managed to get the satellite data or DM data, TANDIMEX, so that's from German Aerospace Center. So that was much more detailed than the DMs that we had before. And we found this peculiar annular landform had like a rim around it, uplifted rim and an uplifted middle bit. And it just strikes out from all the other landforms that we ever saw or encountered on the nullable plane. So our question was, is that related to karst or whatever it is? Like, would be interesting to find out. And just to show you how it really strikes out is like, even if you actually do the cross section, it is different, but I'm still talking only about like 5 to 7 meters. So this is the nullable plane. When something lifts up about 1 meter, it looks like a big alpine place in Europe. We checked just like out of the curiosity. So this is like the dot, the highest elevation of that little landform, and the highest elevations are only occurring like on the north part of the nullable plane because it's slightly uplifted. The northern bit is slightly elevated from the southern bit, but it doesn't really like look like a remnant of some kind of erosion or whatever. This is the satellite image just simply from the Google Earth, and all these around is the rim, and you can see the trout in between and the middle bit, which is the uplifted hump. So you can spot it, basically because of the planes. But when you're in the field, this is how it looks like. So this is just a simple photo. And if you have a strong imagination, so that bush, the blue bush, is actually growing on the rim because it's stony. So that's the big rim. And you can probably spot a little bit of a hump right here. So this is how it looks like really in real time. So no offense if no one else actually ever discovered it. So really like the Tandemix helped us. So cool. The question was, what is it? One of the things we quickly thought about, but we were wrong, is that some kind of a dias or some kind of a dough line that was just like Ridley shape or whatever? So we do have dough lines or dias, which are called like really shallow in sub-arid landscape in an nullable plane, that have sometimes a little hump in between, which you can actually see everywhere here. But that happened because there's a little bit of a bush there, and the Tandemix data is not cleared, so we actually always have a little bit of a hump in the dias. And furthermore, this is not really that readable, but if you've got a big imagination, this is a circular rim we're talking about, and you can actually clearly see it here. And these diases are these little bright spots all around the place. And these bright spots also occur within a landform, which, because these landforms are formed really slowly, we actually like start understanding that this peculiar landform we're interested in must be actually quite old. You can also spot the diases within the big circular future, which is actually made by drone, but this is 1.7 kilometers across, so it was a little bit hard to actually make any clear pictures out of it. Imprinted ridges and swales, which I talked a little bit at the beginning, somehow seem to avoid these landforms, just like you can see in the Namib Desert, actually, like the longitudinal dunes can avoid certain topographical features, like on their way. And that gave us an indication that this landform could have been there for quite a long time. Cool. So because it's circular, we couldn't actually explain it in any other way, we actually thought it was a crater. Impact crater, extraterrestrial crater. Nullarbor has been exposed for 14 million years. Something could have happened over there, and there's been a lot of meteorites found over there. So with this stuff, we compared it to the Wolf Creek crater in Australia, for example. And have ever of you seen the horror movie in Australia, Wolf Creek crater? If not, or whoever you saw it knows that when it happened, a group of backpackers had a car that broke down over there, and then really bad things happened later on. But anyway, our car broke down right at that place when we were actually checking the landform, so that was one of the indicators it could be a crater. However, there was a couple of other, one thing that's important is that the craters usually don't have a central uplift unless they're really big. But we did find a crater in Chad, which is apparently like the same size as ours, and apparently also this doesn't work anymore. So if you can just press the button. Apparently it looks very similar to our landform. So we thought like, okay, it could be an impact crater. Onwards. Yeah, now it's gonna be a lot of onwards. So what we did, we needed a geological proof. We collected a couple of rocks right from the place that we found the landform and all around the Nullarbor onwards and onwards. Oh, cool. And we see, so one of the things was just to check like chrome and cobalt and nickel, and we couldn't find that none of the numbers were like really larger than we actually found all around the place. So we couldn't actually find anything really special that would be a telltale story that this is a crater. Even one of the samples, which is actually a paleosol that we collected around the crater showed a little bit of the higher amount of chrome, but actually like the minerals over there was saying that like it couldn't really go through much of the pressure because they actually wouldn't survive. So we also searched for the shocked quartz, of course, couldn't find any, but at that stage we discovered a bounced on fabrics. So that was one of the things. We knew that the nullarbor, which is actually a seagrass meadow carbonate deposition, we knew that it had a little bit of corals as well, but these bounced on fabrics actually told us that something was growing right on that spot. So we actually like got back to the beginning and not thought about this like as an impact crater, but that because of that something was growing on the place, and maybe we're actually going right at the beginning of the limestone deposition, and we thought about the bioherm. So the bioherms, now all around the world, deep sea, shallow sea, whatever, and we found the only geological proof that could tell actually was that bounced formation. So we said, okay, this is a bioherm, and when we actually looked at it with a little bit clear pictures from the Australian Great Barrier Reef, we found quite a little bit of similarity. So we do have like a central uplift and a rim around it. We also compared it to the Great Barrier Reef in Australia and Queensland, and the annual landforms do form like towards the inland. So here is like the edge of the coral reef. And right now, today, we have annual landforms also with a central uplift right there. So I compared this, and I was a little bit afraid that McNeil should be a little bit angry because we did it, because we weren't really sure what we're looking at, but she also completely agreed. So we were just continuing the story. I put the Great Barrier Reef in Australia into the horizontal way and compared it to the nullarbor. So we know there's a reef over there on the nullarbor, and this is like all the inner place we're talking about, and that's the similar scale of the Barrier Reef right now in Australia, and you also see lots of features right now like in between. So it makes a story make sense. The only problem was, for a conclusion, that why is it just one? So there's one hump that we discovered and nothing more. It happened after a long search, actually, that we found a paper from 1995 that they were actually mapping on an nullarbor limestone different bioherms. Of course, we never saw this paper before because the nullarbor plain is up here and this is all underwater, but it's all the same limestone. So here we go. We do have bioherms also around the other places. We might be just so lucky that we only discovered one. But we didn't stop there, we just moved on. And because we knew what we were looking at for, we actually discovered lots of little humps now on a different part, but somehow in the same place on the nullarbor plain, which we now believe are also bioherms or part of the ancient coral reef. And this is where our research actually stopped and continues hopefully next year because we need to prove it geologically. And this is it. Thank you very much.
Thank you very much. Very impressed by Dolinas. Some comments or questions, please. No? Okay.
If you go back to Joe Jennings again,
Yep.
he actually spoke about annular depressions, but these were with granite cores, and they're in Western Australia around the margins of the plain.
Yes.
A different scale, but karst, not lithology.
Yeah, the granite, you mean? Yeah, they do appear on the western side, yeah.
The granite is emerging through the limestone.
And it's got a little bit of trout in around it as well, yeah. I didn't actually mention that we double-checked everything over there, even in magnetic maps, just in case there wouldn't be any granites or volcanics, and nothing really happened. But yeah, that's agreed.
Thank you, Matej. So we will move to the next presentation by Rajacic and Bocic, and we go back to Dinaric Karst in Croatia, please.
Hello everybody. I'm happy to see you in such a big number here. I wish to thank you to organizer to give us opportunity to present our small research in some karst poljes in Dinaric karst. So all we know that corrosion and chemical denudation are leading process in karst, but also we sporadically have some erosional processes and forms. So we noticed in karst poljes in Croatia alluvial fans as forms resulting of accumulation of eroded material from the slopes of the karst polje basins. And in the literature, we found numerous examples of alluvial fans in karst, but especially in contact karst or in some small poljes, usually regarding to some glacier or fluvioglacier influence. And we decided to check a little bit in our karst poljes to found out some data about these alluvial fans. First, we were very enthusiastic and we should check a wider region in the Naira karst, but we found a lot of issues with this job. So we finally mapped alluvial fans from 12 karst poljes in somewhere in the middle part of the Dinaric. In Croatia, we call it Lika region. Plitvice lakes are somewhere here, Velebit mountain is here, so just for orientation. So we use this approach. First, we should identification in the rim of the bottom of the polje. I must admit that we didn't do it very precisely because there are, you know, a lot of issues and contact with polje bottom and slopes sometimes are very clear, but sometimes not so clear. Alluvial fans are one of the reasons, but there are a lot of other reasons. So we skipped these issues. We just vectorized rim of the poljes just to have some data for about surface area of the polje, just to compare with alluvial fans. Next step, we did it much precisely. So this is the most important part. So we make identification of alluvial fans. So we use digital elevation model 5 meters. Unfortunately, we don't have LiDAR. It's already mentioned. So, but 5 meters, was enough, or it's the best what we have for now. We made some additional maps from digital elevation model, hillshade, slopes, and so on. And we also have quite good topographic maps, 25,000. And approach was that we make visual identification and manually mapping or vectorization in GIS. Next step was when we mapped all what we saw alluvial fans. We found the input point of the alluvial fan, and then we determined the drainage basin. This was made automatically with approach flow direction and flow accumulation, and we defined the drainage basin for every alluvial fan. After that, with this data, we provide some basic analytics. So these are results. In these 12 poljes, we found 38 alluvial fans, different in size, and 42 drainage basins. So one can ask, it is not the same number, because some alluvial fans have double or even triple drainage basin to feed this alluvial fan. These are some examples. We don't have enough time to explain every one, but this is, for example, the larger alluvial fan. This is the numerous alluvial fans in one particular polje, and so on. These are surface area of alluvial fans. The biggest one is almost 25 square kilometer. In this plot, we omit this because it's too large. So rest of 27 are shown here. They occupy total area of 84 square kilometers, and average area for every alluvial fan is 2.2. If we again omit the biggest one, these 37, the average area is 1.6 square kilometer. If we look in every karst polje, we have a share of bottom cover with alluvial fans, but this plot is probably better because these are absolute numbers in square kilometers. So we see that in some poljes we have important area covered with alluvial fans, in some poljes almost nothing. And this is a relation between surface area of polje and share of alluvial fans. We have slightly that small poljes have better chance to have more alluvial fans, because alluvial fans are specific surface, not so big, and in the big poljes they don't have so much influence. And these are drainage basins. They are a little bit bigger, so they are 3.77 square kilometer average every drainage basin for one particular alluvial fan. If we compare alluvial fan surface and drainage basin surface, of course there is some relation that bigger fans have a bigger drainage basin, but it's not so good connection. And if we compare average surface, we can see, total surface, we can see that drainage basin cover almost double than alluvial fans, which is not so expected. Then we provide some morphometrical analysis. I will show you here only hypsometry, but we did slopes and so on. This is this plot shows the vertical range of the drainage basin corresponding this alluvial fans. We can see that, of course, drainage basin have much bigger vertical range. On this plot, we have alluvial fan surface area and elevation of drainage basin, elevation range. So we can see the bigger alluvial fan have drainage basin, bigger drainage basin elevation range. This quite logically. For every drainage basin, we calculate hypsometric integral. It's according to Strahler, and range of values are from written here. So it's not so wide range, because theoretically integral can go from 0 to 1. Here we have some middle values. But when we plot here, we can see that the drainage basins are more with lower integral below the 0.5. So it can be interpreted that maybe are they not so young and active. They are a little bit not old, but mature, maybe middle age crisis. If we compare with geology, unfortunately we don't have lithology map, and we can use this stratigraphy unit map. The problem is that some stratigraphy units have different lithology in one unit, so we cannot see is this some area limestone or dolomite, because it can be both. But on prevailing lithology in some unit and our field experience, we can see that we have two groups of this drainage basin. One group is here on the slopes of the Velebit mountain. They are developed on the upper Paleozoic clastics and Triassic clastics and dolomites. And this second group is here. These drainage basins are developed on mainly late Jurassic dolomites. This is the detailed view on two neighborhood poljes with drainage basins, so you can see the drainage basin are developed in late Jurassic dolomites. So for the conclusion, I will not read all this summarized data here, but I would like to stress that obviously alluvial fans are also significant element of the landscape of the dynamic karst poljes. They are approximately 10% of surface of these poljes. And main factors for the formation and development of these alluvial fans are local relief, high vertical range and slopes, and of course lithology, clastic or dolomite, specifically late Jurassic dolomite. Thank you very much for attention.
Thank you very much. Thank you very much, Neven. There is time for some questions. Okay.
Neven, thanks for your talk. I was just wondering, because these alluvial fans are brought to a planation surface, which is active actually. You know, they are, I guess, dissolved, just as the polye is. So do you think there is some kind of statistical morphometric difference between fans on polyas and fans on some other areas where you don't have, maybe when they are not exposed to actual dissolution at the water table or things like this?
Actually, I don't know in this moment. I suppose yes, and this is our goal to some of the next phases, to compare with some others alluvial fans. What we saw there in the field, these alluvial fans are not active and some are relict, and we see the traces of corrosion on the rim of the alluvial fans. So these data are what we see now and what is visible in the morphology. For some alluvial fans, I suppose that they are covered with another kind of sediment, so they are maybe bigger, but down there below the level of the polye.
Okay, thank you. Some other comment, Uroš, perhaps? No? Yeah.
So on the southern part of Likopolje, some alluvial fans are of fluvio-glacial origin. You have like huge terminal moraines just above the polje, and this sediment is actually forming those alluvial fans. And yes, Franz asked about the influence of water table level in the poljes. Sometimes you have abrasional terraces within the fans. If you would observe on Krbovsko polje, the alluvial fan, it has a couple of abrasional terraces because of the flooding of the polje.
Yeah, thank you.
Okay.
Thank you. Regarding the South Lika polje, for now we just we just take the recent drainage basin. We omit the karstified part, but of course we know that in the Pleistocene, during the Pleistocene glaciation, the lot of water come from the top of the Velebit mountain and move the sediment. Thank you.
Thank you very much,
Thank you,
Neven.
Nadia.
Now we move to the next presentation. I almost forgot that it's my turn, so. Okay, we go back to the place of the crime. We were here with the Karst school excursion a few years ago. We were visiting the cave with a lot of white and yellow clays there, and that time we didn't know the origin. But lately, we somehow connected to some volcanoes eruption. So we go to the classical karst about Trieste Bay. Grafova Yama is there, and this is how there's a cross section from the sea to the Kras Plateau. Here you have this Kras Plateau, which is elevated and then uplifted and inclined due to geological history. And this is the part of this cave. And just down there, there's the main sinking river to the Kras, which flows underground from the Ponors in Scotians caves, where we will visit it on Thursday, towards the springs here. It's about 35 kilometers. So Grafova Yama is on the top of the hills. You remember that we walked from the bottom of Dolina from this Divača fault zone up to the Grafova Yama, which is actually a relict cave, partly unroofed. There are some unroofed parts, and also in the slope of the hills we can find the cave sediments. So there are many clays filled in pockets and in notches. They are everywhere, the yellow one, and they are always covered by the reddish one. There are more, so always the bottom here, and they are covered by the reddish clays. So in another, you always found them also below the flow stones. Also here, the yellowish, the reddish. They are filled in all fissures almost. In some places, they are completely white. And so we did the multidisciplinary studies of these caves, of these clays, and we started with the mineralogy that we already known during our field trip years ago, and it is complete. We can find that these yellow, white clays are presenting the Montmorillonite clay, and the reddish one, it is from different. This derives from the Flysch, actually, and there were some samples which were just weathered speleo attempts. But because they were yellowish white, we didn't know because they were weathered to the clay size. So this is the Montmorillonite, and it is so clean in some parts that it was taken for a standard by the XRD team. And there are really just a little bit of accessory minerals, and we had to wash more than 100 of kilos of this clay to get really small amount of heavy minerals and quartz grains. So the water flows here through underground, as I mentioned, about 35 kilometers, and there are many caves at the active water flow, and there are many relict caves and unroofed caves in this area, and it is the plateau is inclined from the south west towards northeast, and the sediments in these caves are mostly derived from Burkini Flysch. So this is this Eocene impermeable rocks of Eocene Flysch sediments. So they are eroded by Reka River through the karst towards the springs here. So they have in unroofed parts and in active parts and in old parts, all the sediments have the same mineral composition. So they derived from the flysch, and they are different in age. This we saw already from the Aurel presentation. We found them in the, here we go to the first day excursion in the active part of the water, then flow then in the these relict caves which still remain, and there are in the unroofed caves. So this is the cross section, this is the active part and the relict part, and all of these sediments have the same sediment composition, but you can find that there are different in ages. Down there, there are now recent ones, they are a little bit older, and they are from 5 to 1 million years old, and you can see that the river was in the past flowing in up about 150 meters above the present level and the flooding now, and that these dolinas, collapsed dolinas, are much younger. So, but this we can discuss in another paper, but sediments here are about plus minus 5 million years old at the top and recent in the down. And there is in the vicinity Paleokarst, which is Upper Cretaceous in time. It's about 70 million years old. So, but Grofova-Yama, this is higher, and we didn't know how old is it. So first we did the geochemical studies, and we compared the geochemical composition by the closest volcanoes. One of them from northern Italy, Marostica Hills volcanites, and Smrekovec volcanites from the north of Slovenia. And we find out that they are very much like this Smrekovec volcanic, just erode, due to the erosion, they are a little bit more or differently weathered. So we also dated these clays, and we find out that there are about 20 million years old. That means that this is the closure of the closure temperature of the apatite, and we also dated that Montmorillonite with potassium argon dating, and we got about 23 million years old age, and that means that this can be not linked just by the geochemical composition, but also by the dates, the age, to the Smrekovec volcano, or some volcano nearby the Periadriatic lineament, because just lately, and it's not published yet, in Croatia, they found the stratovolcanoes near Varaždin, which have about 600 meters of tephra. So that could be also related to the same type of volcanism from the same time. And we also found it, it's not working. Can you help me? Okay. We found also some zircons, and there are about 14 million years old. That is another volcanism and another time, but that means that the clays were still on the surface when this zircon was sedimented there. So if we look, the Grofova-Yama is here, Smrekovec is here, and the Croatian volcanites are here. So that means that the massive subaerial eruptions of the Smrekovec stratovolcano were presented there, because this was the underwater volcano, and or perhaps from this Varaždin part, and that was the intense trend north trade winds in the upper Oligocene to lower Miocene, and that means that there was perhaps not Alps already, which were not so high in that time. So this was the transport way. And we also did some paleomagnetic studies, but this is still under the consideration and interpretations, but we think that these yellow clays were transported into the caves when the tephra was already weathered into the Montmorillonite in the alkaline environment, and that was happening after 14 million years ago, somewhere, so in some younger episode, and we think that it was related to some regional uplift which started already that time, and that the red clays, they are younger because they have also very different origin. And we think also that the tephra was deposited on already a shallow karst, so some kind of corrosional plain close to the water table, where we could have the water very close in karst, and we think there was not flysch in the very vicinity because there is no accessory minerals deriving from flysch. So, and the tephra was weathered, we don't know when, but could be also during the Miocene maximum, 70 million years ago or later, but for sure before it was retransported into the caves, into underground. We are not sure it was that brought by the small stream. That could be, but not with the big river, because there will be then the bigger catchment and more other minerals associated with, or it was just infiltrated through the karst into the underground. And it went through different stages, and that still stayed there. It is just because that part was a long time, I think, covered by this sediment, so was protected against the denudation, and so it could remain there. So it was protected, so it went through all these stages, because we also have the speleothems in between the white clay and red clay, and we couldn't date them because they were too dirty, or the uranium lead, it didn't go well. In Australia, we tried to do it. So they are much older, that is average of the cave existence, and so we think they are from the very, from Miocene time, where actually the terrestrial environment existed, and it is proved in the intramontane basins of the Deneric karst between 17 million years ago up to 12 million years ago, when they were filled by big boulders and erosional sediments, because in that time there are detecting of some first regional uplifts, and because of that they start to close the basins. So from that time it is also should be our karst time. So we think that even all of these tectonics and corrosional surfaces which are now present, and they are much younger than this Grafovayama here relict. These are some dry valleys which show that the uplift of the area started and water went down into the underground. So we don't know from which part the later sediment arrived, the later flysch, and where was the flysch 20 million years ago. But we are sure that was not very close, because in other way it should be part of the clay which was filled into the cave. And yeah, what else? So this is the trend of the uplift, so it's much more uplifted in the southern part than in the northern part. And for the conclusion, I can just highlight that Grafovayama is extremely important, because it's till now the oldest cave which is still functioning as a part of epikarst, because there is still the solution through the epikarst. There is still growing of speleothems. They are from different times. We have to do the dating of them if there will be possible, especially the younger times. And so far, in no other cave in Kras, we didn't find such an amount of montmorillonite. They are just a little bit time to time in these allogenic sediments, but they are not deriving from this tephra, but they are deriving from weathered flesh in different environment as a illite or kaolinite from the same allogenic sediments. And the cave is actually the relic evidence of the existence of the caves and karst from that time. So the transport in the cave was then through developing epikarst during the first or initial stages of tectonic uplift of this area and into the corrosional planated karst landscape, or by the small sinking river, as I already mentioned. And so it is also the indirect evidence of the nature of activity of Smrekovec volcanic center, because we thought before that was just under sea, and that were just a few eruptions which tephra was spread to some other places. And so we also think that the Alps were not so high. That's another evidence from that time, because there were these different directed winds like is now. So we have to work more on the develop of the karst geomorphology and of this area, and to see how it's related the morphology of now existing karst and the karst from Miocene, because this is just a small relic and all the other is already denuded. There is no more evidences of these old karst surface features, of course, and no more other caves from the same time. So thank you very much. Okay, I think I was too long, 1 minute, so excuse me, and if there is some question, please ask me during the coffee break, which is now half an hour.
some coming really late, and we were waiting, and then everything fell apart at some point. But please really don't be late, because we will go at 2:30. And also, you saw it's quite hot outside. You can grab a bit more water, like I said yesterday. It's, it's kind of needed these days. And this is it. For the other excursions, please, up to tomorrow, you need to make sure to enroll yourself at the registration desk. It's the last time possible, because we are already tight on our buses. Thank you.
Okay, thank you, Astrid. We'll go on. First, we will listen to the recorded presentation of Dr. Ira Sasavsky, A Role of Geologic History and Basic Factors in Karst Models.
Good morning. I would like to thank the conveners for allowing me to make this presentation, even though I can't be with you there in Postojna today, which is a great disappointment to me. To start this session on geology and modeling in karst, I'd like to first talk about a non-karst area and introduce a concept that geomorphologists frequently use. Every landscape that we see and every terrain that we experience on Earth has a history which has shaped it. And our work is to decipher this and to take that knowledge that we gain from examining it and to use that for creating models that are useful for prediction. And in many cases, going back to the basics is very helpful. That's what I like to emphasize today. This image that we see up here on the screen is from Curry Village in California. This is a granite valley in Yosemite National Park. And we see some beautiful cabins and a nice forest there. And we see a bunch of angular boulders around there, very scenic. Of course, what we should be thinking about if we're acting as geologists and being aware of the time factor is how did those boulders get there? And this is an example of one of the recent reasons they closed Curry Village, because time and timing matter. And we'd like to emphasize that as we go through the talk today. The character of any karst system, likewise with any geomorphic system or hydrogeologic system, is wholly the result of these three factors: structure, processes, and time. And by structure, we mean structure writ large, that includes things like the attitude of the rock, the boundaries of it, the internal factors, and so forth. Processes, of course, many things that can operate on it. And time can be both duration and changes that occur through time. So coming back to this time component, which of course is the core of geologic history, is very important for interpreting karst systems. I'm going to start by reviewing a few karst conceptual models, and then we'll go through some other things about ways that hydrogeologists have generalized and synthesized the way the karst community has. Show you one example of a site that we thought was simple, wasn't, and then go into our summary. So onto the karst models, and these are all conceptual models. There's many others that we could have included, but just for time, we can't do that. But this is a nice one that Ford and Ewers put together back in the late 70s, and I particularly find it compelling because it really brings in the time aspect. Not that others haven't done that too, but in this case, they were looking at the effect of fissure frequency and the effect of relief to indicate what different types of caves would form. The left-hand side diagram shows the fissure frequency, and the right-hand side shows these four sort of states that a cave might evolve in depending upon what the conditions are, either a bathyphreatic deep looping cave up in the top or an ideal water table cave, again, depending upon the configuration of the hydrologic system. Will White in 1988 in his textbook put together this diagram, which is really pretty simple, but I wanted to illustrate in here the three things that he found compelling in terms of what drives the development of karst systems. And those are the chemical driving force. Do we have the PCO2 in particular, or some other agents that can be dissolving? What's the physical driving force, which is really the hydraulic head driven by gravity, and what's the hydrogeologic setting? Smart and Hobbs in '86 were more concerned about aquifers than cave development, and in this publication from the National Water Well Association, they put together a very simple but very useful carbonate aquifer model that had three axes. These were recharge, storage, and flow in terms of characterizing what the how the aquifer would behave. And from this, they were able to put forth some recommended development strategies, excuse me, for developing water resources. And you see that depending upon where in this 3D continuum the aquifer lies, there might be different ways you would develop, like either using the spring head or a well field and so forth. And they also extended this into management problems, which had to do with either flooding or pollutant transmission, because karst aquifers do vary quite a bit. And then the last example we're going to look at here is one that Art Palmer put together in 1991, and I apologize that the highlighted bars are shifted for some reason here. But he looked at a lot of different limestone caves and was able to really pull from here the idea that it's the type of recharge and the dominant type of porosity, or perhaps you might say dominant type of initial porosity, that guides the type of caves that we do develop in different settings. So taking from these and also from others, what are the possible significant parameters? If we put this into the structure, process, time context, structures include lithology, the discontinuities certainly, boundaries, orientation, and relief. Processes are manifold, including deformation, how are we dissolving or removing the rock, where's the recharge coming from, and so forth. And then finally, the time aspect, how much time has elapsed? In other words, we consider this to be a youthful system or a mature system, but also we need to consider changes in conditions. We should not think of these systems as being static because things change through time. So what have the non-karst hydrogeologists done to sort of generalize and synthesize these big ideas about the ways that these systems evolve? Well, there's two that I want to outline here. The first one on the left is by Heath, 1984, Groundwater Regions of the United States, and we'll look at that in more look at both of these in more detail. And the second on the right had a more specific purpose for standardizing pollution potential, and that's the drastic system, which has been adopted by many others and modified, and has actually, there are karst varieties of this. So let's look first at the drastic. This is an aquifer vulnerability system, and typically it's based on a concept of layers, and the drastic stands for these parameters are listed here: depth, net recharge, aquifer, soil media topography, impact of betozone, and hydraulic conductivity. And the idea is if we can sort of extract information on all of these layers, we can come up with a summary aquifer vulnerability map, which then allows end users to make informed decisions about how to protect the resources that are there. Heath's paper, which was the first one that we talked about here, is really really a fantastic work at Groundwater Regions of the United States. And what he did was he put together the idea, and of course this is just for the United States, but it has been done in other areas, that different areas could be characterized by typical types of hydrogeology based upon their underlying materials and also what conditions they had been subjected to. So for example, we see in the upper part of the of the diagram, we see a big glaciated central region where the geology may be quite similar to other parts of the United States, which are non-glaciated. So he separated these out and characterized each of them and made a very nice publication, which is useful for both professionals and end users. We should note that his region may be discontinuous or overlaid. So this is his alluvial valleys groundwater region, which shows the major river valleys. So for an example region, his region number 10, the Atlantic and Gulf Coastal Plain, is highlighted in black here, and it consists mostly of interbedded sand, silt, and clay, which are draped upon the craton. Florida Peninsula in the bottom right is excluded because it's a bit different than the carbonates. And with each of these example regions, he has quite an extensive text that describes the hydrogeology and also a diagram which shows sort of the nature of the deposits. In this block diagram, which is greatly vertically exaggerated, we see we've got these layered aquifers with some salty water in deeper parts of them. You can see the recharge zones and so forth. So very, very, very useful. So what have karst hydrogeologists done to generalize and synthesize? Well, we've done a lot, but maybe we can do more, and I guess that's sort of the point here of our discussion. So one document that stands out, back in 1972, Herrick and Stringfield put together a book, Important Karst Regions in the Northern Hemisphere, and this was not so much on the concept that Heath used, but more sort of other regional bent that sort of looked at different areas, but still very useful. And of course, we've got many examples of sort of more detailed publications, such as the Caves and Karst of the USA book by Art and Peggy Palmer, which breaks out the regions by the geology and is useful both for cavers and for karst scientists. But I would say that probably the broadest approach that's been used is the World Karst Aquifer Project by Nico Goldscheider and colleagues, which the sort of end result of the map result is illustrated here, which shows the aquifers, and of course there's supporting paper which talks about the characteristics. And this is certainly a step that's very useful for planners, for conservationists, as well as for the karst scientists. And maybe this is something that can be built upon to go into more detail than we currently have, to end up with something like the Heath report, where we could look at what the specific parameters are that characterize certain karst systems. Now, I want to shift gears for a minute here and go into an example of something that we thought was a simple karst site, but that turned out not to be so simple. And it's just sort of as a cautionary tale. This is from pretty close by to where I live in North America, the Bellevue-Castalia Karst Plain, which is a very low relief plain. It's up in here. This is a map of Ohio karst areas, and Ohio is not very well known for its karst. There's not a lot of dramatic stuff, but we do have a lot of limestone that's exposed along the structural arch, which is present in the western part of the state, Devonian and Silurian aged carbonate rocks for the most part. You can see here where we are in North America, just south of Lake Erie. So each of these red dots is a known or probable karst feature, and in the darker areas, it says, well, we could have karst features there. So this is an area that's been studied for a long time, but we went back and took another look at it just to set the physiography. So here in Ohio, we have the glacial maximum boundary, which runs along here. We have the present day drainage divide, the northern Great Divide, where drainage up here flows to the Great Lakes drainage, out to the North Atlantic, and drainage below flows to the Mississippi River drainage and out to the Gulf of Mexico. And then we've got our study area up here. We'll look at a cross-section of this in a minute. So I want to point out to you, first of all, that this is a hugely exaggerated cross-section, 200 times vertical exaggeration. This basically is a flat area. Okay, you drive across it, it's like a pancake. But to the northeast, we have Lake Erie. To the southeast, we're at the Great Northern Divide. And we've got this gently sloping topography, which is going north towards Lake Erie. We've got, karst areas in here. We've got some river incision. We have a zone of flowing artesian wells and springs, which is down here close to the lake and even in the lake. And we have a coating of till on top of everything, including this area that's labeled as a lake plain. We've got large artesian springs that breach the till cap. This one is Miller's Blue Hole, which the discharge and total dissolved solids are indicated there, and you can see it's got sort of a milky blue color because at this time of year it's precipitating calcite out. These springs, very highly mineralized. If we do some back calculation using Freak, we can actually figure out how much rock removal is going on. 20 cubic meters per day of rock is being dissolved here. Mostly this is anhydrite and some calcite and some de-dolomitization going on. So we have this present-day karst flow system that seems like it's very active because we've got all this rock removal going on. The stratigraphy is here, so the stuff near the surface is the Delaware and Columbus limestones, but down below we've got potential complication. We've got the Salina group, which does also have some carbonates in it, but it's also got a lot of anhydrite in it. And it's quite a thick unit that we've got there, over 200 meters, close to 200 meters of thickness. On the surface, we've got these springs that we talked about, like the one illustrated here. We have very large, irregular sinkholes, and these are a subject of study, because they're sort of oddly shaped. They're shallow, but they're big. Note the scale down here. This is a 1 kilometer scale bar, so these are pretty big sinkholes for the mid-continent of the U.S. This is a picture of one of them, which is actually a swallet called the Big Sink. There are not typical caves known, and by this I mean we don't see typical solution caves. What we see, probably the best example on the right, is Seneca Caverns, which is actually shows no evidence of dissolution in it at all. It is completely due to collapse. And you can see there's a bedrock in place here, Columbus limestone and collapsed bedrock right here. This is a commercial cave. And when we see exposed surfaces, I don't have a good photograph of them at the land surface, but this is one that is sort of similar to it from the western coast of Ireland. We see sort of enlarged joints, these clints and limestone pavement. We don't see really enterable caves unless we have collapses. So what's going on in this system? It was originally thought that this area, the reason why the karst is sort of so odd is because it was glaciated and the glaciers came through and scraped everything away. But when we reflect upon what the paleohydrology was, that's probably not really the whole story. And by that I mean when we had the ice sheet present, the maximum at 22,000 years ago, we had a great thickness of a wet-bottomed ice sheet, glaciers on the periphery. And in our study area, we were looking at 3 to 4 kilometers of ice thickness. And with a wet-bottomed glacier, we would expect very high hydraulic heads of end-glacial and subglacial water to be pumped into the groundwater system, which is underneath there. And when we think about what that would mean, you know, this huge head which was present here, which is, you know, now removed, it's completely melted back, the Laurentide ice sheet. What that would mean is we would be having this groundwater recharge systems where we would basically be pushing in all this undersaturated fresh water through the carbonates and down into the salina group, and doing all sorts of crazy geochemistry there in terms of dissolving those units. So going back to this diagram, what we have in the present day, you know, in the paleo day, we had this, you know, huge ice sheet up here, and we had groundwater flowing in this direction. Now we've got groundwater flowing back to the north to the Lake Erie drainage, but not very much is flowing. And the reason why is because we've got this till cap and we have a low gradient. And so it turns out that these large karst springs are actually discharging fairly ancient water, which is highly mineralized, but is only coming up in a few places. And so the karst system that we see here, well, the sinkholes are almost all due to collapses down into the salina group with some suppositional sinkholes near the surface in the till, but the remainder of it is really just sort of a static system with this highly mineralized water sitting in it. So to summarize and to close up here, it's useful to think in the construct of structure, process, and time whenever you go into some new area, whether it's for a consulting job or whether you're doing some academic research to try and decipher what the processes have been. Using this geomorphic construct allows us to sort of compartmentalize things and make sure we're not skipping something. We shouldn't consider systems as static. The example that we gave here, you know, was a glaciation where we had, you know, a very major change in hydrogeology, but there, of course, are other changes that go on through time, like changes in rainfall, changes in vegetation, changes in climate, and so forth. And then finally, wouldn't it be great if we could develop a karst regions guide that sort of breaks these out in the same way that Heath has done, and it would be useful for both for our own professional purposes for sort of putting karst aquifer and cave development in this broader context, but also be useful for land use planners. What might they expect in certain areas? Would we expect diffuse flow aquifers? Would we expect conduit flow? And what sort of protections should we afford? So, thank you very much.
Okay, we'll go on with the next presentation of Professor Ford. And now for something completely different, morphology and deposition of the main sulfide ore in Proterozoic dolomites in Canada.
Thank you, Madam Chair. Yes, I'm going to take you way back in time to the Precambrian and look at something decidedly odd, but very speleological. Let's see if I can operate this machine. We're going up to, well, with the arrow, this is I can't get the pointer to function. Anybody?
Pointer is here.
That one. Okay, thank you again. Well, you can see where we are. We're in northwest Baffin Island. It's supposedly an example of Mississippi Valley type lead zinc mineralization in orogenetic forelands, as you see from the citation from Bradley and Leach. It's an old piece of work that I did in the 1980s, 90s. I was asked by the a mining operation, nanocivic, the Inuit word for the place, or the place where they find things. It's along the strike of a horse block. You can see the horse here, and the Graben Strathcona Sound in the background that is frozen solid. What we see in the near ground is the mill at the center of the, there we go, in the center of the picture, at the mouth, the western end of the body. Once or twice, late in the summer, a boat can come in to the dock down on the shore. You see beautiful downtown Nanocivic. It's all dispersed now. There is the entrance to the mine. These are the typical highly insulated dwellings, and this is the storage on the dock of the concentrate that's been processed at the mouth. About 600,000 tons of ore per year from 1976 until the thing shut down in 2000. So I have here the perfect site for an aged geomorphologist. The mine is blasted shut at both ends. You cannot get in and see what features it contains, so you have to rely upon my interpretation. Okay. Sorry, I'm making it. Oh, there we go. What about the caving, you ask? It's by pickup truck along a single adit, straight through the strike of the Horst deposit. The mine temperatures you can gauge from the color of my nose, about minus 13 Celsius in the winter. You can't work the walls in the summer because during the summer the walls are covered with hoarfrost, as like here in Grot Valerie in South Nahanni that we've worked on intensively. Stein Erik's been there. So I had to go in the winter when it's, as you can see, it's pretty chilly. Here's the map of the situation. The ore body is truncated at both ends by much later valley cutting, but the scale here is quite wrong. That's 0.5 of a kilometre, and 1 kilometre. So we've got a 3 to 4 kilometre long main ore body. It's flat and horizontal in a horse block of Precambrian age. Here's the structural situation. We have upper Proterozoic shales below with a lot of sulfide in them, and again cover shales above, a little bit of block faulting, the formation of the order 400 meters thick. The ore body is here. It's truly horizontal over its area, and in the past, when this deposit was in place, it will have been covered by the later shales. I studied the many cross-cuts. The mine was approaching the end of its life. You can see the structure here, a central cavity, minor fluctuations off cuts. It's very flat. It's a horizontal channel at 300 meters above sea level, 3 kilometers in length, 5 to 7 meters deep. It cuts discordantly across the 15-degree dip of the dolomite. The channel's about 100 meters wide, the central 75 reaching ore grade. Its roof is damn nearly flat as far as I can make out from the many exploratory drills that the mining operation did. It's less than 2 meters from the strictly horizontal. So it's now jacked up 300 meters above sea level. It's late Proterozoic, and it's still nearly horrible. The the geologists who investigated thought that it was a phreatic level with an entrenchment below, but the drilling below shows a possible second level at about 250 meters in some of the drilling operations, but highly irregular. There's no suggestion of an entrenchment. The thing is hypogene in great detail. One of the things that fascinated me here were the fins of bedrock. The bedrock is dipping at 15 to 20 degrees, sticking into the rock. In a normal cave, we expect fins to develop in a good river passage. Maybe if they're a bit clay or less soluble, they will project up to about 5 meters, agreed. In nanocivic, with sulfides, we've got steep dip. The fins are cut strictly against the dip, both from the south side, the north side, 10 to 25 meters sticking out, as displayed by the cross cuts, and a mixture of flat, horizontal deposits, the sulfides, to widely waving displaced sulfides that obviously collapsed or slid off of the rock. Here is an example, the miners have blown it up for us, of a bedrock fin on the south side and the ore body laid on top. Bedrock fin on the north side, similar. They're very unlike the normal fins we see in any limestone cave. Here are some examples from nanocivic. I measured in the cross cuts. The scale bar there is 5 meters, I'm sorry, so this thing is a fin about 20, sticking out about 25 meters. Compare that to fins in conventional, or solution in conventional caves, a slightly acidic notching. If the notching is more extreme, it goes deeper. Occasionally we'll get a situation like this where the roof is beveled off in an acidic solution. There are 2 types of paragenetic development. Starting when we start with a passage at the base, it works its way slowly up, reaches a control level, and spreads out there. For the fixed water table case, the case that applies at nanocivic is a variable water table, a long still stand here, more rapid ascent, rather descent, ascent of the water table, which means descent of the bedrock mass, so that we see 2 successive masses, the ore being plated out on the base below. It's the product of corrosion notching in highly acidic solutions. Look at this picture I've drawn for you here in one of the cross cuts 18. The first is a slash about 1 meter deep, a slash of regularly layered sulfide, chopping up the carbonate, bulky material, blocky, massive sulfides below, layered material, layered sulfides, onlapping onto the fin here. It's a pretty standard pattern of paragenetic development. excuse my shaking, I'm struggling with a cold and infection. I was fascinated by the fins in the bedrock that we see. Take this example at Crosscut 16 South. An upper fin, it's sinuous. A lower fin beneath it is similar. The edges show that the solution that was dissolving the rock was creating a sinuous or meandering cavity with a wavelength of about 50 meters. At several places, there are at least 2 generations of fins. The similarity to fin development in salt, the most soluble of rocks, not dolomite, almost the least soluble of the conventional karst rocks. This is a salt mine in Cardona in Spain. You see it's highly deformed stratigraphically, but we get these regular fins slashed in. The same kind of thing is done in dolomite at Nanosivik. I recognize 4 sedimentary facies in the mine. The first are settled or precipitated on and parallel to the floors or with onlap onto the sloping surfaces, this kind. The second are chaotic polymic breccias that suggest episodes of cut and fill. The deposit is being partly eroded away again and is sliding off of the fins on the side into a vacated central place. This is an example of fairly regular deposition. Here is an example of chaotic deposition. Sorry, yeah? Oh, got it. Please excuse me. Here are some good examples of the relationship between thin deposits of the regularly layered sulfide and the fins. And the greatest example is here. We're looking in a main mine, 425 meters to the north at precisely the same level is a small northern tongue, and in between is about a 1 meter thick sheet of the upper regularly layered pyrites, the horizontally layered pyrite sheets. They're slashed by corrosion into earlier deposits, into the dolomite. And lastly, there's some metasomatic replacement of the dolomite, primarily on the upper surfaces of the fins, but occasionally below. So we took a look at the source and evolution of the ore fluids. The host rock plots here a tight bunch on a Del 18013C plot. You'll see that there is a wide range in the Del 180 and Del 13C measurements in the categories of the dolomite and calcite precipitated with the ore inside the cavity, suggesting a considerable variability over time and spatially, mainstream and on the flanks of the stream of water flowing through in the ores. The fractionation suggests temperatures in the range 90 to 150 minus 40. Temperature reconstruction was not so good back in those days. It should be much improved with the new season of work. Rising to 250 in the late stages. We published that back in 1991. Here are Del ranges from a number of the Mississippi Valley type ores of North America and elsewhere around the world, Illinois, the Gulf Coast, Michigan, Alberta, and you see that the hours range very, very widely across a number of the fields. So here to conclude is my interpretation. We have a first ore fluid paths coming up, hitting overlying shale roofs and in a sinking graben. And later on, there's a second ore fluid path that deposited some calcites to the south of the region. I considered three models: a pre-existing cave, rejected, a model towards emplacement of a fixed surface, and then finally the one I settled on, emplacement towards a rising interface, that is either liquid and gas or density or significant density difference inside a liquid rising, so that as a consequence of the horse structure sinking. There was a great still stand essentially at what is now 300 meters above sea level. Whether it was a genuine water table or, albeit very hot, fluid, dense fluid and steam above, or whether it's a density controlled fluid level at greater depth, I don't understand. I preferred the gas-water interface for many years, but my opinion is tending to shift, and I'll be most interested to hear from those who have other experience. Very quickly, during the last glaciation, before the last glaciation, we had a solid ore body here in green. It's covered by a glacier. The glacier develops, a tributary glacier to the south develops a stream that passes through the ore and brecciates it for 300 meters along the south side, considerably increasing the cost of mining on that part of the operation. And the perils of working in permafrost, it's cold. The parts of the milling house began to collapse. They had to build these giant supports, and you can see ground ice growing rapidly into the mining tunnel. That brings me to the end, ladies and gentlemen. Just to look at the weather as it was in mid-February as I was flying back out again to the warm and effete south. Thank you.
Thank you very much. We don't have time for questions, so we have to go on. Please, the next is Gibert et al. Sediments in a hypogenic underwater cave, an indication of high flood periods in the past.
Hi everyone. I see now this is my time to fight a losing battle with this pointer stuff. I'm Dénes Siebert, coming from the Budapest University of Technology, and I really feel honored and also hopeful that you can help me. Preparing the material for this talk, I realized that at the end I have much more questions than answers. So, okay. I'm a lazy man, so I did this work in a cave, which is about 10 minutes cycling from my university. So quite under the built-up areas of Budapest on the hilly side, the western side of the Danube River. To tell the story about the geological situation about the cave, it's a quite usual one. The sea came, deposited some limestone in the Eocene era, and the sea went and then came back again, deposited some marl and clay, and gave the opportunity for the formation of some really nice hypogenic caves at the border of the limestone and the marl, more or less. This cave I will talk about is completely or almost completely submerged, and it has no direct surface connection we know of. So the theory is that it's a completely hypogenic cave formed by mixing corrosion from deep thermal waters rising up, and not rainwater, but some regional waters arriving at some shallower path. Okay, maybe the most prominent feature of the cave, if someone enters, is that the water is crystal clear. The visibility is only limited by the light, and divers do not experience any flow there. So it's an almost no-flow cave. Of course, sediment transport can happen if we kick up the silt. And there is plenty of silt to kick up at the bottom. In some passages there are more than 3.5 meters thick. We know about it because we have probed it with the rod, and it was that long. So it might be any longer. The question is, of course, if we have this lot of sediment, where does it come from? 2 years ago, I had a student, a new student, not a very bright one. I thought I'd give him a very safe topic for the BSc thesis. So the topic was to compare the dissolution or residue of the walls of the cave and the sediment below. And of course, I thought that the two will be the same. End of the story, nice BSc thesis. Of course, it was not. It was very different, so we decided to probe it a bit more. We have taken core samples with the help of PVC tubes. And of course, we had to improve a little bit on the technique because the sediment was very loose. It was not compacted at all, so it did flow out of the tube. So we made a nice inflatable mechanism. Please click the video. Sorry, not. Yeah. We could insert the sampling tube quite easily with hand, and we inflated a balloon at the bottom which held the sediment core, and the only remaining task was to carry this sample out of the cave without too much movement, so it's not mixed up. Okay, and the results were these sediment cores. We did freeze them so we can push it out of the tube without disturbing it or compacting it too much. We have dried them in the horizontal position, cut them up, and there was this absolutely stunning stratification observed inside. There were maybe two features which were very prominent. One is the rich color changes along the length, sometimes in less than 1 millimeter thick layers, sometimes forming several centimeters thick layers with very different particle sizes as well. We did recognize some of the constituent of the sediments, especially the more coarse ones. There were all kinds of remains from the Eocene, Eocene shallow water life. There were sea urchin remains, pieces of seashells, foraminifera, etc. And we have found pyrite, which is present also in the cave, but not in a very large amounts. But what still remained as a kind of secret was the origin of the different colored clay layers, because we did not see that much clay in the dissolution or residue. There were quartz particles, and the amount of pyrite was also a kind of mystery, because we have seen a few examples in the cave, but absolutely not much. So we decided to investigate it a bit more to give it a bit more numbers. We have characterized the particle size distribution in some layers, and really there were absolutely different distributions from the clay to the really coarse sand region. There were even bigger particles, but the instrument was measuring only up to this particle size. And because we did not believe that this residue was carried by the current, the observable currents in the cave, we revisited the flow velocity measurements, but yeah, they remained very, very small. And we just compared the situation with the diagram, Hillstrom diagram, to see where we are. Actually, the prominent particle sizes and the flow velocities are quite well in the deposition region. So indeed, there should be no sediment transport at the current state of the cave. If we could reproduce the speeds in the past, we should be somehow around here to carry all the sediments which we observe. So we have tried to age the sediments just to know when this sediment was deposited, but we did not find any plant material. We really had very high hopes of this aragonite, because these small crystals look like as they were grown in the sediment, but we did not find any difference with the radiocarbon dating. In the cave, we have some small critters, some small snails living, which were quite a challenge to find because they are also smaller than a millimeter, but we did not find them in the sediment, so we could not use them for the aging. And yeah, we still have some hopes of these black spots, which we determined as pyrite, but framboidal pyrite, so they might grow already when the sediment was forming. Yeah, at one place we have found this really nice vertebra. As you see, it's not properly a cave bear, it's much smaller. It's a 0.5 millimeter scale, what we see here. And the largest sediment particle I have found in the cave was this. I told by paleontologists that this is a sub-recent dog skull, so means that it died somewhere in the last few hundred years. But unfortunately, none of these things were in places where the sediment layer was present, where the sediment layering structure was visible. Okay, the only suggestion maybe for aging the sediments is the presence of the very, very fine layers. These layers are quite different, found just one hill away in a thermal bath in a freshly formed carbonate sediment, and they exactly know when the bath was built, so they know the age of the sediment, they could date it, and these very fine layers are marking the high levels of waters in the Danube, so they are about twice a year or something like this, as the Danube level was pushing back the water. Okay, but we decided to give this a bit more numbers. So we investigated the chemical composition, maybe the iron because of the color, and the calcium just to see how many limestone we have, and the insoluble parts. And we have found all kinds of variation also within one column. And also we have taken more samples. We have tried to sample the whole cave with sampling points as far away from each other as possible. And we have found that in the large parts of the cave, so in the large corridors with cross-sections of more than 10 square meters, a very similar layering is present. Of course, the thickness of the layers are a bit different, but we don't see the same in the smaller corridors, and we don't see the same in the newer parts of the cave. We also have checked the thickness of the sediment layers just to see whether we see some indications with not the current but the past flow directions. And we have collected all the data in a database and tried to do cluster analysis on this. And maybe the biggest thing we have learned about this, that the color and the particle size are completely uncoupled. So iron minerals are present also in the fine and in the coarse parts of the sediments. And maybe the most important thing to take home is that in the past, we don't know currently when, the flows in the cave are much higher than we could expect from a hypergenous cave. So I expect that maybe later we will find some relict sinkholes above the cave, which prove that the water was entering directly from the surface in the past. Well, I would like to thank everyone who has contributed to this work, and I'm really, really open to questions and maybe to answers as well.
Okay, maybe we have time for a short question. Please, Filip Odra.
Wait.
Okay, thank you, Dennis, for this nice presentation. I have two questions about the source of the sediments. Did you make some mineral analysis showing it could come from the upper Mars or from the Danube? And the second question is, in case of high water in the Danube, I don't know how high it can go, 2 meters, for example, you may reverse the flow gradient, and in that case, you can push inside some water from the Danube containing sediments from the river.
Yep. The analysis, or some of the analysis we did, was that maybe the clay parts matching the marl, which is above the cave, and of course the clay layers as well. Also the pyrite could come from there. And about the second question, the Danube level is only, well, there are for sure some springs under the Danube. And the Danube, as the head grows, pushes back the water from these springs, but the actual water of the Danube doesn't reach the cave. At least that's what we see now. What was in the past, I don't know.
Okay, I think we need to stop here. Thank you. I'm calling Anna Mladinovic and Jelena Čalić. To what extent reactivated faults are or are not responsible for karst processes, example from Serbian Karpato-Balkanids?
Good afternoon, everybody. I will present some data about related to the investigation of impact of reactivated faults. Why is that? because when I started to be a caver as a structural geologist, I was always thinking about what is the impact of the fault structures on the karstic process. And when you are reading textbooks in geomorphology, of course, first thing that these books are mentioning is that the karstic process is related to of course, water that is acting on certain rocks, carbonate rocks, through a certain period of time. And one of the most important part of that process or this cave formation or karstic formation is the structure. And when we started to do our investigations in this eastern part of Serbia, in this part of Carpato-Balkanites, I saw some really nice examples of fault structures, which are very prominent there, like these ones. But when you go to cave there, in that area, what you really see in reality is something like that. Of course, when you are thinking about structurally controlled cave, some romantic version would be that, which is one of the most beautiful structurally controlled caves I have ever seen. It's located in Istria, but when you go to field in the Carpato-Balkanites and see some structurally controlled cave, it's something like that, where you have these cave passages in some very narrow areas, probably related to some fault gorges or fault rocks. So why is that? Geological structures, of course, they control the development of karstic process, but when we are thinking about geological structures, we should always think about the type, of course, of the structure, then kinematics, if there are some kinematics, and of course dynamics, and incorporate time. There are some very nice examples of development of these karstic joints along some joints and sedimentary structures. But when we are thinking about development of karstic process in these fault rocks, we are always dealing with something like that, which should or tend to be not so well for development of karst structures. So to see where we are working on, this is the Carpato-Balkan orogeny. It is located in this eastern part of Europe. And when we're thinking about tectonics of this area, we should know that through the central part of the Balkan Peninsula, from Belgrade down to Thessaloniki, and from Belgrade along the course of the Sava River, we have the suture zone of an ocean that existed through Mesozoic time. It was a Neothetis ocean, and everything which is western from this suture zone, it's called the Deneric orogeny, where we are located now, somewhere here. And everything eastern from that suture zone is called the Carpato-Balkan orogeny. The central part of this Carpato-Balkan orogeny is located in eastern Serbia, and it extends, of course, in the southern part of Romania, and in Bulgaria and North Macedonia. Carpato-Balkanites are relatively simple orogeny, which were formed and were active from Cretaceous to Miocene times. and we investigated several deformational phases, and the two of them were active from Oligocene to recent times. The first one was related to the formation of large strike-slip faults, which dominates in the Carpato-Balkan area, and they were active in the Oligocene in the Miocene times. These are the very famous, actually, Černožiju and Timok faults with a cumulative displacement of up to 100 kilometers, which is very much. And the second tectonic phase, which is active also in the recent times, is also related to the activity of these two faults. We investigated also fault structures in the caves, in the karstic caves of this origin, and what I will show in these presentations is related to three most prominent caves, which is located in the northern part of the Carpato-Balkan origin in Serbia, then in the central part, and in the southernmost part near the border between Serbia and Bulgaria. This area is also very active today. Actually, when I say very active, it's very active for this continental regime. We see that there are earthquakes, of course, in this area also nowadays, because yesterday it was some earthquake here. But when we see focal mechanisms of earthquakes and the fault activity, we see that in these southern parts, faults are strike-slip or transpressional, and when we are going to the upper part, to the northern part, they tend to have a normal component. This is also evident in the caves. So I'll show the caves the cave structures or the fault structures in the investigated caves. The first cave in the northernmost part is located also very near to the epicenters of two earthquakes that happened some 10 years ago. Also the structures, geological structures inside the cave also indicate that the cave passages are related mostly to the faults and the big fault zones, because most of the bigger fault passages, cave passages are located in these fault gorges, where not only the dissolution of the limestones are present, but also the mechanical erosion of these fault gorges are responsible for the formation of these cave passages. When we are looking at the central part of the investigated area, we see that most of the bigger cave passages are also related to these fault gorges, and there is direct relation with these big and regional important faults. One of the most beautiful is this cave passage or this one, but also we have places inside the cave where we have these fault gorges that in some way can stop or decrease the karstic process. It is like here where we have also the clay minerals inside the fault gorge. And what we see here is that this cave, for example, is related, its strike is related to the strike of the fault, which is regionally important in this area and which is probably active in recent times. And when we see the southernmost part, you can see that there are a lot of thrusting in this part because it is the termination of this strike slip fault and the horse tail structures are forming there. So we have multiple active thrusts in this area. When you see the geological cross-section, you can see these multiple active thrusts. So our investigated area was located here in these Jurassic limestones, which are located here near these thrusts. And what we see here is very narrow passages, very short caves. They are related to the faults, but also the fault rocks have a lot of clay minerals which decrease karst process and could stop that karst process. So when we are thinking about tectonic structures and their relations with the karstic process, of course they can positively affect the development of karstification, but the multiply active fault structures with the development of fault rocks that have a lot of clay minerals can also decrease karst process and even stop it. The importance of regional faults in terms of the development of karst conduits can be very discutable, and occasionally I can hear that people are talking about cave passages that are related to some regional faults, and very rarely we actually see that on the field, so we have to be very cautious when we are talking about that.
Okay, thank you. We have time for a short question, if there are any. Doesn't look like. Maybe we can discuss later. It's an interesting topic. So now I'm asking the next presenter, Slapnik, with the title Reddish Paleokarst Multiphase Infillings in the Megalodontid Bivalves and Solution Voids in the Julian Alps of Slovenia.
Hello everybody. Today I would like to represent this paleokarst multiphase infillings in the megalodontids and solution voids in Julian Alps. What we're with the presentation which will follow to first of I will talk you some purpose of the research, then where we are, and a little bit introduction, and then we go to the methods and to the results, when I will be first talking of the infillings in the megalodontid bivalves, and then I will talking about the comparison of these infillings in the megalodontid bivalves and in the corrosion voids, and then some conclusions. So what was the purpose of the research? It was to examine the origin of these infillings and age, and then define infillings generations. Where we are in Slovenia, in northwest Slovenia, in Julian Alps, in the Podpisky Valley. Here. Megalodontids are typical for the Norian Retian Dachstein limestone, occurred in the Lofer cycles. Usually they are filled with early diagenetic white calcite cement, but in our case with reddish sedimentary infillings. We are, this is, oh no, yeah, okay. this is picture from the air. Here is our location, these blue parts. And we are so in Dachstein limestone. And we also examined some Neptunian dikes here marked with stars, and also some larger Neptunian dikes here. And this is the main plate of these infillings in the megalodontite. Okay, and also in the section we notice these corrosion voids, which is really similar infillings to the megalodontite bivalves. So with this reddish cement with black pebbles in it. And on this main plate, where is the megalodontidas, red megalodontidas, we have these smaller Neptunian dikes, one of them. And in this other location with blue one, I showed you before, this is this bigger Neptunian dike. This is infillings of this bigger dike in front of us. We defined here 2 generations in it, and this is the wall of the dike here, the Dachstein limestone, and the main plate with megalodontidas is here. So what were the methods? We described and in detail sampled the megalodontids, the Neptunian dike, and we sampled rock sequence a few meters above and below this main plate. And the fillings we watched out under the optical microscopy and cathodoluminescent microscopy, and we did some XRF. So first we were talk about infillings in the megalodontite, and we observed overlapping here and crystal growth in the fight 4 generations, and each generations involves a repeated sequence of void formation and then subsequent infillings with sediment and cement. Okay. So we start with 0 generation, 0 because there is no infillings with red sediment. It's just the thin sedimentary corrosion voids. And then we notice, we define the 1st generation, which have the selective dissolution appears on the primary structures of the shells, and then grow a little crystals with a little brown crystals and white, and then after that is infilled with this 1st generation of cement, which in this cement we find rare ostracods and some foraminifera. And this is under the cathodoluminescence, so the structure we see it here. And then a little crystals and shines a little bit different under the cathodoluminescence, like here this is black first on the structure, and this brownish one, it's different color here. Then was the 2nd generation. This was bigger dissolution in the shells, and started growth with this bigger cements, bladed cement, and they were in the top white. And then after this growing, these cements, the infilling with calcite 2nd generation comes in with clast, and it's oftenly laminated. So we have here on the field, a picture from the field, and this is from the optical microscopy, and this is cathodoluminescence. And here we see the 1st generation of cement, like really in the structure, and then up and then growing these little brown crystals and white, and then comes inside the 1st generations of infilling, and then on the top of this growth with this bigger bladed cement with white top, and then after this, the second generations of this laminated calcite with lamina. And we saw also under the cathodoluminescence the difference between this first generation and second generation of the cement. And then we have the third generation. It's different from others. It's different because it's not filled the voids, but filled the cracks between the host rocks and also the older phases of the infillings. We see it here. This is the third generation. So, okay. And we now go to the comparison of these infillings in the megalodontite into the corrosion voids and Neptunian dikes. This is pictures from the field. Really similar in the field that the corrosion voids have similar infillings that megalodontite. So we did a really simplified model, like this is rock, and this is corrosion voids example, or the megalodontite, and it's infilled like just with this sediment with black pebbles, or some geopetal structures, or filled completely with white cement, or started to be geopetal and then infilled with later generations, some of them laminated, and this is remarkably similar to first and second phases in the megalodontite. So under the microscope, it looks like this. This is from infilling from the megalodontite, the first generation, and this is from the corrosion. These two below is from the corrosion voids, and really similar composition we see. And then we have the comparing with the second generation. This is second generation in the megalodontite, and below pictures are in the corrosion voids, really similar with laminated and similar clasts. And then third generations, so really different. But here is the key indicator that is different, the planktonic foraminifera, who occurs in the middle Triassic and up, and Protopeneropsis on benthic foraminifera, and also some glauconite and non-transmitted minerals, so on. And we found really interesting other infilling with Globotruncanas in one Neptunian dike in the main plate with Megalodontidas, and in some corrosion voids also Globotruncanas, and three species are matching here. So we have much younger infillings. So for the conclusions, the first three generations are formed under the subaerial conditions, meteoric water, and with strong corrosion. This goes for the early diagenetic processes. And in third phase is completely different, indicates us to the mechanical crushing of the rock related to the formation of this Neptunian dike, and it's much younger than other three. And we have the open end because of this finding this Globotruncanas in the voids and in the Neptunian dike. And we are still curious because we sent the samples of the cements of the Megalodontidas to ICP-MS to determine ages. So thank you for your attention.
Thank you. We have time for questions. Somebody wants to add?
Did you find any subaerial exposure surfaces?
Yeah, I hear you.
Did you find, because these are underground karst features,
yeah.
Did you find any exposed palokarst surface related to this subsurface
yeah, we
features.
have intent to go this summer to watch for this surface in here in this location. So yeah, it's still in plan.
There are also some a little bit bigger, let's say, erosional voids, like meter wide. Did you study also this one? Yeah.
Yeah, yeah.
Are they similar?
This big one was filled with this white calcitic cement, just without infillings. Or we missed something, maybe. No.
Thank you for your presentation. Between the early diagenetic processes of the first phases and the last one in Santonian period, do you have an idea of paleo environment? Was it always marine or shallow marine, or was it continental immersion with karst development? Do you know the
yes, so this first three generations, 0, first and second, was in this inside, yeah, this we see. Yeah.
Okay, thank you. We'll go on with the last presentation of Boštjan Rožić with the title The Enigma of the Oldest Allogenic Sediments in the Unroofed Cave Loza.
So I am the last one to struggle with this stick. This might be an addition to the talk that had Nadia before, and surely it's an introduction to the afternoon excursion that we will have just after this talk, because it's exactly in the area that we will visit. I will talk about the chert pebbles from one unroofed cave. They're not only chert pebbles, they're also some other siliceous rocks, as you will see, but main focus was on the chert. We'll stay here a bit longer because we need some, let's say, just brief introduction to the geology of the area to understand what we were doing. So we were actually trying to find the provenance of these chert pebbles. Here in the intersection of the southern Alps and the Dynamites. Postojna is here, and this is the southern trust front, and this is Dynamites. And generally, the stratigraphy here goes like this, that it's quite common until the Middle Triassic. For all areas, we start with some Variscian Ras, which is brown here, and then we go to the carbonates. Especially in Dynamites, we have this stable platform that uses a lot of carbonates, which you know exactly what I'm talking about. But there are some events between, some clastic events in Carnian, and also this is important, it's the middle Triassic rifting event that produced small-scale basins and it was accompanied with the volcanic activity. If you go to the southern Alps, and above is Flish, which you probably also know. It's characteristic for this area. If you go to the southern Alps, it's a bit more complicated from Middle Triassic up. We have the deep water sediments here with typical deep marine sediments like deep shales, sedimented carbonates, and rhodolarian shells, stuff like this. And then we have the Juliard platform, which we just visited a few minutes ago. And it was also producing carbonates for a long time, but not so long as Deneric, until the end of Lower Jurassic, more or less. And then it was drowned to become a submarine plateau. That's it. This is a simple geology of Slovenia, and now we will go on. Where are we? We are just positioned here, south of Postojna. This is called Slavenski Rnik. It's karst plain with the direct contact with the Eocene fish, and from this Eocene fish, the water Kuliščica, sorry for this. It's flowing inside. We have some ponor caves. And here in this area, there are these sediments that flow inside. They're typically composed of the altered eroded flysch components, but this area is characterized by active ponor cave, and then we have some unroofed Lonza cave here. It's quite long, and it shares the sediment history with the active ponor cave. But there is one location here which has a bit different sediment, and we will look now to these sediments. Okay, right. So this is from present-day sediments. They're made of flysch. This is unroofed lava cave.